This is going to be an intro to shaders for people who already kind of know how to code, but not code shaders specifically. So this is kind of the basics of how the assets in Unity are defined. This is different in different game engines. Frag shader retrieves data from the vertex shader if you want to, and then you also output a color. Okay, let's try to get an overview of what is actually happening in this one. The data you get in the mesh for the UV coordinates is literally just the coordinate of each of these vertices. So now you can see the normal of each vertex on this one. So here we go. We have something that looks like it's lit by some light source, right? You might want to have this range right here because we don't want it to be super dark. If our maximum is sunlight, you can specify the color of the surface. The color of the light source is still going to affect this. So if we give that a color. So these should point toward the camera, and this should be in world space. So we can again, if the view reflection is pointing directly towards the light source, we want it to be very strong. You may have noticed that this is extremely faceted, right? There we go. So now we have like this very, very sharp edge. Wherever the value is 0.25, I want it to be 0. Wherever the value is 0.75, yeah, that works. So now we're tracking the mouse position. The mouse position is intersected with a mathematical plane. So that makes sense, right? Now we have these things moving, and now we have these things moving out from the shore, right? This one doesn't have any shoreline like generated data. So I have like a bunch of like parameters to control, you know, how soft should the blending be between the blobs. You can also like change the way the fractal works to like alter it and modify it and whatnot. Yeah, so everything kind of follows from that. It's very similar to any other racing game in that, you know, reach the finish line as quickly as possible. This is spline based. You create segments like this. You can move them around, manipulate them the way you wanted to. It's a very interesting level. Then slap in some checkpoints. Status live. All right. I'm gonna wait for people in chat to confirm that things are working. I hope my mic works. Hope everything works. I stayed up like super late last night trying to get the streaming set up to work proper because I just like swapped out a bunch of components. It is working. Super. Thank you, Unsettled Games. Seems like it's Gucci. Thanks. Oh, right. My glasses. Heck. Welcome to the pre-stream where not much is going to happen except talking to you and you letting me know if things are broken. So for those of you who are here, what's your experience with coding in Unity in general? Like, have you done shaders before, or like have you done coding before at all, or are you like brand new to coding as well? Making a game would never really dig into shaders. Gotcha. Oh, Rickful, so you did coding and used 3 major database editors, ShaderPart, ShaderGraph, Amplify. Awesome. Then you probably know, like, this is going to be super easy for you. This is probably going to be a bit too basic, because I'm thinking I'll probably start from, like, the very beginning. I don't know how much I'm going to go into, like, how code works in general. I think I'm going to assume that people vaguely know how to code. Otherwise, this might be too slow in general and difficult to, like, I don't know, move forward. Independent tutorials plus node-based editors. All right. Yeah, okay. Node-based editors are, well, I'm obviously very biased, but node editors are good. They're like, there's a lot of like shitty things within shader coding that's just like boilerplate and like annoying things you have to set up just to get it to work, and annoying things you have to like remember, right? But yeah, so node-based editors kind of let you do that more easily because it like handles all of that automatically. So you can like focus on, you know, what you artistically want to express in the stuff that you're doing in the shader, right? I worked with Unity at several game jams and in my internship. Never done shaders apart from a failed attempt at Unity's shader graph thingy. Gotcha. Will I upload the VOD to YouTube? Yep, I will. Assuming everything goes well and nothing like bad happens or whatever, I'm gonna upload this to YouTube, yeah. But yeah. Hello, fur. Or there might be a cat walking by every now and then in the background. Thank you for the subscription, Fake Swede. Heck. There's a lot of people chatting. I'm not used to this. I'm excited to see how we teach shader basics because I have a hard time knowing where to start when trying to get people into it. Yeah, that can be difficult. Because it's like, where do you start? Like, if people know coding, you start in a very different way compared to if they don't know coding. Because if they don't know coding, you need to kind of like start with coding fundamentals in general, right? So then you need to go over like, oh, what's a variable? What's a function? What's a loop? And whatever. Yeah, so it kind of depends on like what your audience is, which I guess would be super useful for me to ask you. Like, how many of you, um, how many of you have coded before, or how many of you have not coded before? That would be super useful to know. Does the stuff we're going to learn apply to 2D as well? I think so, yeah. How do I gauge this? It depends on what you mean by 2D. I think the stuff that we're going to through is not directly applicable to the 2D sprite shader in Unity because that one is kind of complex. But yeah. So thank you so much for the subscription, Migormer. How did I pronounce it? But yeah, thank you so much for the Prime sub. Okay, so most of you have coded, it seems like. That's good. That's going to make this tutorial way more fluent. Right, and it has music. Hold on. Let's assume we know coding, otherwise we won't learn shaders today. Yeah, exactly. It's going to be like, either it's going to be too slow, or it's going to be too fast for people who don't know how to code, or people who don't learn super quickly. Like, I think I can like do a quick rundown on how to code, like very densely packed information, but then you need to like exactly like follow along to 100%. What version of Unity are you going to use? I'm probably going to use 2019.1. I might... It doesn't really matter which one you use. The things we're going to go through is not really pipeline specific. So this is going to be like how shaders work in general and kind of the basics of shaders. So it's very much a beginner tutorial. So we're probably not going to like go into... we're probably not going to go into like specifically how to set things up to work with Unity light mapping and stuff. I think what my goal is, I want people to have an understanding of how shaders work in terms of the structure of a shader and the basics of that. Because I think after that point, it's easier for you to learn, you know, how the Unity pipeline works and any other pipeline, I suppose. Is your OBS recording this? Yes. Make sure you use royalty-free music if you want music. Switch will mute the VOD and they will not be able to upload it to YouTube. I'm recording 2 audio tracks, so I'm just going to cut out the music for the YouTube version, and I'm not going to care about the muting on Twitch. That's fine by me. So it's the VOD is primarily going to be a YouTube thing. Okay, so we kind of decided that this is going to be an intro to shaders for people who already kind of know how to code, but not code shaders specifically. So I'm gonna assume that most of you know what a function is, what a variable is, and so on. Do you need to import anything to follow along? It depends on how you want to follow along. If you want to, you can get Unity and like follow along. Yeah, go for it. If you don't want to, you don't have to. I think I'm gonna run through this tutorial by not assuming that you're following along. I think yeah, I'm probably gonna do speed ahead and not like wait for you to like and confirm that the things are working on your end and whatnot. I think I want to go through a lot of theory, and then if you need to go back to like repeat something, this is gonna be uploaded to YouTube later. Yeah. Let's see. I wonder how big a part of this I'll be able to translate directly to GLSL. Probably a big part of it. I mean, all the like parameters and inputs and properties and stuff like that is probably not going to be translatable, but anything that's inside of the vertex shader and the fragment shader is probably going to be almost directly translatable as long as you just swap out the words, because they use different terms for the functions. Let's see, 2018.3.2, very specific version. How long do you plan on going for? I plan on going for however long I have energy for. But I think my streams might like average around like let's see, It's 4 hours, I think. So we'll see how long it goes. It also depends on like how engaged you are, if you want to like ask a bunch of questions and whatnot. So yeah. How did you get started into shaders? I think my first shader thing was probably in the Unreal Engine. Wait. My packages are sad. I need to start a new project again. God damn it. Delete folder, Unity Hub. Yeah, so I think Unreal Engine was the first one that I used. And then let's see, then from there on, I kind of started learning the basics of all the math you do. So in node-based editors, you kind of just focus on, you know, the relevant parts of making shaders, not the boilerplate and the boring parts, right? So yeah. Also, thank you so much for the raid, Tiger. That is super nice of you. And also welcome the people who are joining. I'm struggling to talk at the same time and create a project in the correct version of Unity. Hold on. Let's see. New projects. 2018.3.2. No, 3.6 actually. There we go. Are you gonna leave the VOD up? Yeah, I think I'm gonna primarily host it on YouTube, so I'm probably not gonna care about the Twitch version. So the Twitch version is probably gonna be muted in every now and then because I'm gonna run music at the same time. But the YouTube version is gonna be without music. So, I want to cast to my TV, but it don't want to work. Oh no. Do you have to cast it? Is there a browser in your TV? Like, can you go to the website directly? Oh, Countryside? Then you probably don't have a TV that has a browser, I'm guessing. Also, I hope you're doing well in the countryside. Okay, let's try music. Let me know if this is too loud or if this is like fine. So I think it looks fine on my end, but I don't know what it's like for you. Oh, also realized I need the music ticker at the bottom. Oh, right, the music ticker is not gonna work this time. Okay. Sorry about that. So, okay, I just don't think I have time to set that up. Is there a browser in your TV? Such a wild statement from me 10 to 20 years ago. Yeah. Like, browser in your TV? What are you talking about? Okay, I'm guessing the music's fine. I haven't seen any protests on audio levels. Okay. Let's see, I need to import Shader Forge, and then I think I'm ready. There was a, I was gonna do an intro to shaders for a bunch of students in Sweden. So it's a game dev school, and I did like a coding thing with both C# and shaders. Anyway, so there was when I was gonna show how shaders work, and I wanted to demonstrate vertex colors, I couldn't get it to work. It was so frustrating. For some reason, it just refused to work. I don't know if there was something with like that version of Unity that was on the computer, or if it had like a weird import script or something, but like it was just completely broken. So that might happen again, because apparently vertex colors don't work when I'm like teaching it to people. I don't know. It's strange. Who needs vertex colors anyways? Let's just use UV channels for everything. Alright, let's see. Where's Shader Forge? Oh, somebody asked if I'm gonna be using any external packages. No. I'm gonna use Shader Forge probably to either to either demonstrate a visual thing or to explain something more quick, or yeah, more efficient explanation, or I'm going to be using it because I need to see the shader code for something that I forgot how to do in code. So it's useful to have ShaderForge for that. So, because there was this weird shift when I was making ShaderForge where after I made ShaderForge, I just started forgetting how to do shaders by hand. Because I didn't have to remember all the terms and everything, so I just used ShaderForge all the time. So there was this gap where I just like, I don't know, forgot everything. Thank you for the follow, Manuel. First time question, what is ShaderForge? ShaderForge is a node-based editor for Unity, which is a kind of a visual and more artist-friendly way of making shaders. So it allows you to make shaders without having to code. You still need to do like know how shaders work and set them up and everything, but yeah. Exclamation point ShaderForge. Why is the background blurry but not the book title Bright Earth? Compression, I'm guessing. I don't know. Softflow, thank you for the follow. There are no dumb questions here. That is very true. Yeah, don't hesitate. Like, don't hesitate to ask questions. Like, if you're, yeah, like, feel free to like ask whatever you want. And if you, there's no need to feel like you're dumb or whatever. You're not. You're just new, right? And we all were at some point in time. So, yeah, go for it. Unity shader coding. I've never seen anyone do that on here before. I've never used ShaderForge, but I've used ShaderGraph. Gotcha. I mean, they're very similar, but yeah. ShaderForge like the alternative from the Unity ShaderGraph. ShaderForge was kind of what existed for Unity before ShaderGraph. So it was kind of, sort of, almost superseded by the ShaderGraph. But there are some like differences in like ShaderGraph, I think, is only tied to specific render pipelines and not the default render pipeline in Unity. So you need to like, I don't know, you need to, wait, I completely lost my thread. Yeah, right. You need to pick the one depending on what render pipeline you want to use, right? I think the ShaderGraph is only available for the high definition render pipeline or the HDRP in Unity, whereas ShaderForge was made for like default render pipeline of Unity, which is kind of just because HDRP didn't exist when when ShaderForge when I created ShaderForge, right? Do you have to have the LW HDRP for ShaderForge? No, exactly. So you don't need that for ShaderForge. So ShaderForge has, yeah, ShaderForge is just going for the default pipeline. The problem with ShaderForge though is that I abandoned it quite a long time ago. So now it's open source. It's available on GitHub if you search for it. There are some compatibility issues because I didn't upgrade it for like Unity 2018 and 2019. There are people who have done like forks and whatnot that do work for that though. I considered updating it and just making an update that's like 2019 compatible and just like leave it there. From the hardest part with shaders to convert a real world problem into shader logic. Do you have any recommendations for that? I mean, you need to go into the math of it, right? Because that's fundamentally what shaders are. So if you have a problem that's like I need something to look a certain way depending on distance to the player, right? Then you need to convert that to a mathematical issue, right? Or rather, like, I want this to be read when I get close to the thing. So then it's like, okay, what does close mean? That means a distance that is under a certain threshold that you consider close, right? So then, okay, so then you translated this to a mathematical issue of like, okay, so the distance has to be under a certain threshold, then I wanted to switch to a certain color, and then you kind of like structure it that way. So you need to like find all the variables that are relevant for the thing you want to solve, and then you can make the shader from that. Which might be difficult because like it's a lot of math to do shaders. This is my problem with ShaderGraph because I can't layer cameras, which doesn't allow me to stop weapons clipping and say in a FSL game. Wait, you can't layer cameras in the HDRP? Huh. Yeah, I mean, you can do that like in the standard pipeline, like even without ShaderForge. Do shaders work independently On the render pipeline. No, I mean shaders are usually very specific to the render pipeline that you're doing, depending on the whether or not that shader is part of that pipeline or not. Foster Kittens, thank you for the follow, and welcome to the stream, and also welcome to the stream, everyone. Heck, there are so many people here. Is there performance impact on having models with extra UV sets? There is a small performance impact. I think it depends on the platform too. I unfortunately don't know too much about like having a certain amount of features to do and how that affects platform performance and whatnot. Thank you so much for the sub, Gillimp. But I do know that, like, for instance, if you're making a shader on mobile, then like I'm pretty sure that if you have UV coordinates that have 4 components instead of 2, that's way more expensive because they have some optimizations and whatnot. But yeah. I feel like on PC it's probably not going to be a problem. There's some nuances in like how batching works and the amount of this gets complicated, I guess, but it depends on how many vertex streams you have and how you can batch stuff. So if you have too many, I'm talking ahead of many of you now, but if you have too many interpolators, that's going to make batching difficult. So yeah. What is this picture? Heck yeah, that looks super nice. Now I'm nervous. People are actually watching this? Oh no. What is a render pipeline? Okay, so a render pipeline is kind of the high-level structure of your game or interactive experience or whatever it is you're working on. So you might have to structure things in a certain way to make lighting be unified, as in use the same lighting for all the shaders and whatnot. Thank you for the follow. To use the same lighting for everything. So then you usually set up a pipeline where you have a common functionality between various different shaders. So if you want to use a very specific, lighting functionality that looks in a different way or a specific way, then you generally set up an entire pipeline to make sure that like everything is unified. If you want to get the name of the current song, you can do !song. The music ticker is a bit broken right now. Yeah, it's just not working. And it might take like 15 minutes for me to set it up, so I feel like it's not worth it. The song is just not going to be part of, or the music's not going to be part of the YouTube recording, regardless. So, how to pronounce your nickname? Ace Gikmo. Is there any books, reading material, video tutorials, course you'd recommend for people wanting to learn shader coding? Yeah, there's one that I always recommend to people. So this is specifically for learning how to hand code shaders in Unity. So this is not like specifically the theory of like how to set up lighting functions and whatnot, but so here you go. This is one that I would recommend to a lot of people in case you want to learn coding in Unity for shaders. If you just want the theory for lighting and whatnot, this is probably not the best, even though it does go through that. But that's a really, really good resource. There's one thing I don't understand in UV data. If we consider UV coordinates as 2D coordinates, what values are in Z and W values? It depends. It depends on the shader. Depends on how the model was exported. We're probably going to get to that. Yeah. All right. I figure we should probably get started soon. Do we? Maybe we should wait like 5 minutes or something in case people drop in like a little bit late. Anyway. So, all right. I just want to say thank you all so much for joining, by the way. It's heck, I hope this is going to be useful. And do like let me know if there's something that I failed to explain or something that was like very unclear. Feel free to like have me clarify, and I'll happily do that. All right. So I usually don't do like specifically streams for like making tutorials and whatnot. What I usually do is that I stream game development of my own game. and then I kind of have a tutorial-like approach to it. So I'm always like, I always try to explain what I'm doing and try to keep it like educational. So while working on my own indie title in Unity, so if you're interested in general about like game dev or whatever, or want to see someone code in Unity or want to ask questions, then feel free to join whenever I'm live. I'm always like very open. Oh, work will probably watch on YouTube, but I love these. All right, neat. Thank you for the follow, Novakti. Oh yeah, we also have a Discord server. If you want to join a bunch of other game developers, we have a Discord for the people following the stream. There's a lot of like coders, there's a lot of Unity people, so yeah, feel free to join. What's your favorite thing that you've done while in US this time? That is not safe for work, so I'm not gonna I'm not gonna go into the details of that. I said I forget to put my. There we go. Thank you for the follow, Great Crawford. That's not what I meant. You asked a very like specific question, and I try to answer it as honestly as possible. No, honestly, I haven't done like super much in the States. The thing is, like, I'm not really here as a tourist. I just live here every now and then. So it's kind of like me asking you, like, oh, hey, what's it like in your hometown? It's like, I stayed at home for the most part. I don't know. Okay. All right. Let's see. This is working. Good. This is a Unity. We're also gonna need, hold on. Need to open all the things. We're gonna Portland in a couple of weeks though, should be fun. Yeah, that's gonna be nice. Let's see, I'm just setting up Photoshop so that I can like sketch things. Because there's gonna be a lot of theory in the beginning. For those of you who are like, to get you an introduction to what even shaders are. What's a port land? It's the land of ports. A lot of boats and airports, I suppose. Airboats. Is that layout recommended or just your personal choice? Both. It's my personal choice, but I would recommend it. All right. Okay. Are we ready to go? Are all of you ready? Should I get started? Or maybe you don't even know how to be ready. Like, what does it mean to get ready? If you want, feel free to like fire up Unity and try to like follow along if you want to. I'm not gonna really design this tutorial as a follow along tutorial. It's more gonna be an overview and introduction to shaders and just kind of like, yeah, getting all the information for that, right? Okay, so let's get started then. Whew, okay. Also, by the way, this is like improvised. I've done like minimal amounts of preparation. So again, feel free to let me know as soon as something is unclear or you need some clarification on like, you know, what the heck I'm talking about. I'm probably going to be using terms that you don't know, and then feel free to just like go, hey, we don't know that. You should know that we don't know this. So yeah. Anyway. Okay, let's start with the basics. What is a shader? I feel like that's something we should answer first, right? Like, we're talking about all of these shaders, but what the heck are they? And why are they important? Why are they needed? And whatnot. Also, thank you for the host. So anyway, all right, so you can think of a shader as code that instead of running on your CPU, it runs on your GPU. So your GPU is the thing that handles graphics and all of that type of computation. So if you make a shader in Unity, that code is going to be on your GPU. So what does that mean? And how is this structured in Unity? So this is like, so let's just go over the basics of what a shader is and how it relates to assets in Unity and what a material is. So All right, so let's say we have a shader. There we go. Excuse my handwriting, but it's just the way it is. All right, let's say you do have a shader. That's usually what does the document look like? Something like this with an S. That's a shader. So this is our shader. So what is this? This thing contains a lot of code. It's kind of like you have an input to something, and then there's a function in that one. So in this case, we have data as an input. Usually that's a use it as a mesh. It's like colors and whatnot. Like whatever parameters you have, you send that into the shader. The shader does some math here. Math. There we go. Perfect. And then it spits out. Generally, it spits out a color for the pixel that is being rendered. So you send a bunch of things into the shader outputs a color depending on how you position the thing on the screen and whatnot. So this is kind of the final color it's going to have when it's outputting to your whatever to your screen, right? Technically the frame buffer, I suppose, but anyway. Yeah, so this math part right here, that's the shader. All right, so let's see. So what's a material then? So shaders, they're kind of like C# scripts, but it's a shader code instead of C# code, right? So in Unity, you make your scripts, but when you have your like game objects and whatnot, and you attach scripts to them, you don't really attach the script to it. You attach an instance of that script as a component, and that component has a bunch of parameters, right? You can usually set like, you know, the radius of something or some, you know, parameter for speed or whatever. And that speed parameter and whatnot is not defined in the shader or not defined in the C# script, right? That's defined in a different thing. And that different thing for shaders is materials. So the material part is this part right here. This would be the material. I cannot type. I'm sorry. Material. There we go. So this part would be the material. So the material tells you, what do we send to this shader? Like what color should it be? What texture should it be? All of that, right? But the shader itself determines what it can actually receive in terms of what types it can receive. Like it receives a texture and a color and maybe a value for something. And then the material defines what we want to send in terms of values, right? So yeah, so materials are usually the sphere thing. It's just a blue sphere, right? So the materials are the shader's inspector. The shader doesn't really have an inspector. It's more, or not the same way as it has components. I can show you what I mean. So let's go to Unity. Let's create a material. New material. There we go. Let's set the shader to something more simple. Unlit color. Here we go. Okay, so this is a material, and you can see the inspector for the material has all the properties of this material. But then this material has a reference to a shader. It says here at the top, shader, and this is the shader that it's currently using. So, but then we can set this one to be red, for instance, and then we'll make another material, and we'll set this one to be green. And these two are using the same shader, but they look different. But they're running the same code. They just have different inputs. So what's happening is that one of these materials, they're sending red into this thing and then into the shader. And then the shader says, okay, we're going to take the color red. We're just going to output it to the screen, and that's the color. And then the other one is going to input green here through the shader, and out we get the green color, at least in this shader. In most shaders, you don't just, you know, send a color and then get the color. So this is like a very, very, very basic color, basic shader, right? At this stage of knowledge, what a shader is there a difference in how you describe vertex versus fragment shader? Yeah, we'll get into that. I'm not going to do that yet, because that gets confusing. Because like, why do we call the functions shaders? I don't know. It's frustrating. Anyway. So this is kind of the basics of how the assets in Unity are defined. This is different in different game engines. Like Unreal Engine, for instance, in Unreal Engine, you can actually apply shaders to objects as well, and they're going to be rendered with the default parameters of the shader. But in Unity, you have to make a material to define, you know, what parameters you want to send to the shader. Yeah. So I think in Unreal, the terminology is like, this is a material and this is a material instance, I think. So if you've used Unreal, that's the analogy. All right, did that make sense so far, or did I miss something? Right, I forgot to mention. So the thing you apply to meshes or objects in the world, that's materials. So if you want to render an object, then you slap on the materials of that object, right? So it's kind of like, you have your object here, or prefab, right? The prefab refers to the material, right? And the material refers to the shader to define, like, this is kind of the the way things are set up. So you can never apply a shader to an object in Unity. That just doesn't work. Think about the follow, Carl. All right. Think about the follow, Arab. Cool. So I think we got the basics down. So for the asset flow. All right. So let's see. Well, what do we talk about next? Right. Let's talk about the vertex and the fragment shader, or at least the kind of the basics of this. So, all right. So we talked about the this shader right here, and it's a bunch of math and it's a bunch of inputs, right? So the bunch of math has a specific structure the way it works, and the data almost always includes a mesh. You have to have some object to render, right? So let's see. Let's go into that. Okay. So here's the basics of how a shader can like render to the screen and how that pipeline works. So let's say you have a mesh, right? So that would be a mesh, because you need an object to render. So say you have an object in Unity, you would just, let's say, create a sphere. There we go. Let's remove the collider. We don't need that. So yeah, here's a very basic mesh using a very advanced shader right now, actually. Let's use one of our basic materials. There we go. That's a pure red material. Okay, so what do we got here? What's the input data? So we have the mesh filter that has the sphere mesh. We have the material in the mesh renderer, which is the new material here. So the input to this shader right now is the parameters you define in the material and the mesh itself. So the mesh and the material, and by extension the color, goes into the shader, right? And the material is by extension a bunch of parameters, right? Parameters. I hope my handwriting is somewhat legible. But yeah, so we have a bunch of parameters that are defined by the material, right? And then these two get piped into the shader. So this is where the shader begins. Perfect. All right. Shader blue from here on. Okay, so if we think about this, well, what is a mesh? Well, what is a mesh built out of? Like, well, when we say that we send a mesh to the shader, what are we actually sending, right? So what we're sending is basically all the topological data, right? So it's the vertices. So you have all the points in the shader, that's all sent, all of the mesh is sent to the shader. And then also the way it's triangulated, right? You know, where the triangles in the mesh are defined. So this data is sent to the shader. So this data, it depends on how you set up the shader, depending on like what data you want to receive and how you want to read that data and how you want to use that data. But generally, the workflow is something like this. You have your shader. Well, what is the first thing that happens? You have something called a vertex shader. So let's start the vertex shader. Vert shader. So the vertex shader is a specific part of the general shader asset, right? So the vertex shader is a specific function inside of this one, where the input to the vertex shader is vertices. So, you know, again, you have your mesh with all the triangle data, right? That's barely a triangle. There we go. That's some triangles. So the vertex shader, you know, as the name implies, takes vertices. It sends all the verts to it. So you can consider this like a function with the input is just vertices, right? Okay, so what does it mean to input vertices? So your vertex shader gets data about the mesh and the location of each vertex, the normal of each vertex, the UV coordinate of each vertex, the vertex color. So each of these has a bunch of parameters, but most importantly is the position of this one, right? So each vertex has a position within the mesh. So you can think of the mesh like like your mesh as a pivot point, right, or an origin. Like here's a coordinate system. So the location of each vertex, you can think of that as a vector like this, right? So that's a position of each vertex. So the position of each vertex is, you have your y-axis and you have your x-axis, and that's the data you're going to get. Also z, because it's 3D, right? So that's useful. So what happens in the shader? Really good at explaining these complicated topics. Thank you so much. I think my first incomprehension about UV is UV about shaders. We're gonna get to UVs. Okay, so the vertex shader. Oh, one thing that we need to note here is that these coordinates that I mentioned here, this is in the space of the mesh, right? So the 0.0 here, or comma 0, this is not 0 in the world. This is 0 of the mesh, right? And that's the coordinate we're going to get in the shader. So the vertex shader has an input of, I guess, local space or model space. Let's call it local space. Local space vertices. Okay, local space vertices, or vertex positions, I suppose. But yeah, so that's sent into the vertex shader. And then what's sent out of the shader kind of depends on how you set it up, but the basics is usually that you take the position of the vertex and then kind of output it to where you want to render the mesh. There's some like weird nuances in how you define positions in the vertex shader, because you need to transform it from local space to where you're placing it in the world, because we want the position to matter. We want that to move the mesh, right? So we need to like define, or we need some way to convert from local space to where you want it to be rendered. Unity has a helper function for this. So you can basically just pass this in to a function that converts it from local space to clip space, which is a space that the vertex shader should output. But yeah. But it basically takes a local space position, applies the transform so that it's in a specific location in the world, and then it converts that to clip space, and then that's it. So, but yeah, so for now, you can just think of this as the input of all the vertex data. All right, so I think this is good. This is getting a bit like too theoretical right now, so I think we should jump into more practical stuff. Actually, let's go to the fragment shader as well. Okay, so this is, we need clip space, coordinates. There we go. Are you going to be talking about the MVP matrix? I never remember the order in which is what. Probably not. I think it's too low level for this, because you don't really need to know it in order to make art or shaders in Unity, right? Okay, so the vertex shader, if you just have a simple shader, you want to render it at a location, this is all you do in the vertex shader for a very, very basic simple shader. The vertices just pass through their position, you convert it to clip space, and then you're good. Okay, next part is the fragment shader. So this is probably the most exciting part. Fragment shader. So now we have run the vertex shader. The vertex shader executes on vertices, right? So you have your vertices in the mesh, and this is what gets sent into the vertex shader. If you're familiar with coding, you can consider the vertex shader like a for each loop iterating over every single vertex. So all the code you define here in the vertex shader, that's going to happen for every vertex in the mesh, right? So yeah, it's like a for each loop. Like for each vertex, do some operation and define where it's going to be placed in clip space. That's the vertex shader. Let's go to the next one, fragment shader. So the fragment shader, instead of running per vertex, the fragment shader runs per fragment or per pixel, more simplified. So okay, you can do things per pixel. What does that mean? It literally does this for every single pixel. It's like a giant for each loop over millions of pixels. But since GPUs are extremely parallel, they can just do that. What exactly is clip space? You don't really need to know that in order to make shaders for this, but very simply put, clip space is a space that is camera relative. So you have your camera, right? And then you have some area of view, right? Here. So this is the frustum of the camera, and so say you do have your mesh, right? These coordinates don't match the coordinates of the camera, because the camera, I forget if the pivotal clip space is in the center or in the base, but basically the clip space coordinate system is this frustum right here. So clip space is the coordinates you need to transform it to behave like a camera, because that's generally what you do in games, right? You don't always have to do that in shaders, but yeah, that's so clip space is this space right here, where you've got, x coordinate 1, x coordinate -1, y coordinate 1, y coordinate -1, or I guess this would be z and x would be the other direction. Yeah, so this is kind of just like a yeah, -1, 1, and so forth, right? So this is just between -1 and 1 on both x, y, z, or all three. Yeah, so that's the clip space, right? And like doing the math to get to clip space from a local space is kind of like convoluted, because you need to like transform between all of those things. But again, Unity has a single helper function that allows you to just like give it local space vertices and it outputs clip space coordinates. So generally you kind of just like run that code and then you ignore it. Like I don't even know the proper order of all like the view matrix and the model matrix and all of that. Like I don't know, and I don't have to know. So I tend to ignore it. Yeah, but if you're interested, there's a lot of resources on, how that whole transform chain works. But I'm not interested in that. I want to make pretty things. I want to make games. So yeah. Great. Fragment shader. Here we go. Does the fragment shader run for every screen pixel, or just a pixel that the mesh covers? It only for the pixels that the mesh covers. So what happens in the vertex shader is that you transform all of these to clip space, right? After it's in clip space, that's when you define where on screen it's going to be rendered, right? So then your screen is going to have, let's say this is your screen, and then you get a triangle in this one, right? Like this. And then there's a rasterization process in the GPU that basically tells you that these pixels are within this thing, right? And then that's where the shader is going to render, and that's how that works. So we just like there's an internal there's an internal process that rasterizes this for you, right? That tells you where to render the shader, right? Yeah. And also, you might recognize this jaggedy pattern, and that's exactly the problem that happens when you don't have anti-aliasing. So that's that interesting problem of like, you have an edge passing through a pixel, and then what do you do? Like, how do we do this? The answer to this is usually anti-aliasing in one form or another. There are many different ways of doing that, but yeah, generally that's the setup and how it's like rasterized, right? So it only runs for whatever's visible on screen. There's also another step where if triangles are outside of your camera, it's actually going to cut this triangle and just not render this part. It's just going to be cut usually. That's the frustum calling. Okay. All right. Fragment shader. So we got our fragment shader now. So what does that do? So this one retrieves data from the vertex shader that you decided to send. So you can send pretty much whatever you want to the fragment shader, or you can send nothing. You don't even have to send anything. So let's say you send nothing, and in here, extreme high res solves the jaggy edges. Does that make sense? Yeah. And there are different ways of doing extreme high res, right? Okay, so fragment shader, you basically input data from the vertex shader, and then the fragment shader in the end spits out a color. And that's it. It spits out a color for each fragment. So the frag shader or the fragment shader is like a for each loop over every single pixel that the mesh is covering on screen, right? Why do you use Visual Studio for C# and Sublime for shaders? Does Sublime have better shader support? I've actually switched off of Sublime now. I should update the thing at the bottom. It's like a year ago or something I did that because there was no syntax highlighting in the Visual Studio, but it does have that now. So now we use Visual Studio for shaders too. Thank you though. I should update the description. How does the vertex shader work in 2D? In 2D, it works the same way. It's just still the same thing. It's still vertices, in Unity at least. I don't know if there are other ways to get around that, but I think you mostly... No, wait, there are ways around that, but I think... But anyway, yeah, generally it's just, if you want to do a 2D sprite, that's just a mesh that doesn't have any depth. And usually it's just like two triangles, and then you have your, you know, character or whatever, right? So that would be... like a sprite or something, right? But it's still a mesh. You still have the vertices here, right? Okay. So anyway, frag shader retrieves data from the vertex shader if you want to, and then you also output a color. And that's again for every single fragment that the mesh is covering on screen, right? Okay, and then the rest in here is, well, quote unquote, just math. Okay, that's a high-level overview of the structure of shaders, materials, the sort of simplified internals of shaders. Does that make sense so far? Are there any questions about this overall structure? I need to drink. If I'm not drinking water, let me know. Let me know if, and I'll do it. Think about the follow, Rivadia. Rivadia, I think. I'm not sure. What's the difference between fragment and pixels? Pixels are physical, like, units on the screen, but fragments are, fragments are a bit different because you can render to something that doesn't correspond to the screen. Yeah, that's fragments. So it's kind of whatever unit you iterate over in the fragment shader, right? And that doesn't necessarily correspond one-to-one to your pixels. I've seen some shader example online with use a vert or a frag function. How do they work? I'm not sure. I'm guessing there's some fallback where they use a very basic setup for the other shaders, or there's just no vertex shader. I don't know. Maybe it's just pass through. So the vertex shader basically manipulates the vertices and converts the position relative to the model, relative to the camera. Pretty much, yeah. It's not really relative to the camera. There's the difference between view space and clip space, but sort of, yeah. And the fragment shader then takes that data and basically says how to blur out the pixel within those vertices. Yeah. There's another nuance in how you pass data from the vertex shader to the fragment shader, but we're going to get into that as soon as we start, you know, writing a shader. Yeah. Okay. For the vertex shader, getting the position of the vertex and offset, is this using the pivot that you set in Maya and offsetting from that? Yeah, the pivot you set in Maya, or Maya has this weird thing of there's a difference between the origin of the object and the pivot point. Like, actually, I guess I can show you. When I have multiple overlapping vert and frag shaders, does stuff go through all vert shaders, then all frag shaders? Pretty sure. I actually don't know. I don't think it matters. Like, the order as a user doesn't matter because the output would be the same. Where does things like displacement and tessellation happen? We're not going to get into that in this case, but there's, if you want to do like displacement and tessellation, you can do another step before the vertex shader, which is the geometry shader. So the geometry shader can also be an input to the vertex shader. And I think that the input to the geometry shader and the output is kind of different. So the geometry shader, I think usually, depending on how you set it up, receives 3 verts defined as a triangle. So this is kind of for each loop over every triangle. And the geometry shader spits out another list of triangles and vertices. So the geometry shader can actually modify the mesh and change the shape of it or something, or add triangles, and then that gets passed into the vertex shader. So that's why the geometry shader allows you to add more geometry if you want to tessellate it, or if you want to do stuff like that, right? Okay. But we're not going to go into that. Plus, geometry shaders are super expensive, so if you can avoid doing geometry shaders, that's probably a good thing. So I haven't done too many geometry shaders. I think I've done twice or something. Okay. Let's see. Any other questions about the overview of this stuff? This looks like humans are banned, but with a square band symbol instead of a round one. Okay, I think we're ready to get started writing an actual shader. No weird dancing. Is this weird? Yeah, it actually does look like a weird dance. Kind of like pivots, spinning around, sort of, because the leg is straight down. Anyway, please stop your Sigma in the cached face. I don't know. Okay. I'm gonna draw the cached face. I'm gonna do it. There we go. Sort of. Okay, good. Let's write a shader. So this was a whole bunch of theory. Looks like that optical illusion where you can't tell which direction the dinosaurs are spinning. Yep. Oh, right. I was going to talk about the thing in Maya. Sorry, I totally forgot about that. Okay, let's see. Say you have an object in Maya, right? You can see that there are a lot of different things happening here with the gizmo, the position and stuff, right? So right now, this object has a position. If I drag this around, the actual position of this model is over here. But generally, when you export stuff, you tend to freeze transformations. So the origin of the world is the pivot point of the entire model you've got, because you tend to have more geometry than just one thing, right? Think for the follow, Ale. Yeah, so it's usually a multitude of things happening in your mesh, right? Let's combine them. But yeah, anyway, so this origin of these models don't necessarily correspond to the pivot point, which is what I was gonna say. Because in Maya, you can actually move the pivot point like this. But if you export this to Unity, this is not going to be the pivot point. So it's kind of there's a separation between where you put the pivot and where the where the actual origin of the mesh is, which can get really frustrating. So be careful if you're making models and whatnot, where you put the pivot and whatnot. I just almost always freeze and reset transformations just to make sure that the pivot matches up with the origin of the models. Anyway, that was a tangent. Sorry. Thanks for the tutorial. No problems. Thank you all so much for joining this whole thing. I'm glad you seem to find this useful, or at least I hope you do. Okay, are we ready to make a shader? I think so. Well, let's do it. Okay, let's just remove the old materials. We're gonna go custom materials only. This one is now sad because this one doesn't have a shader applied to it. Or a material. All right, let's make a shader. So I think the easiest place to start is to go to create and then shader, and then there's the unlit shader. The unlit shader is very, very, very basic. It's got a basic setup of a vert and fragment shader, and we can just kind of get started from there. So simple shader. There we go. Let's open this. One day you want to do customize the shader error magenta, man? Go for it. Sounds like a great idea. Okay, so we had this thing, and you might be like, oh, this structure kind of makes sense. And then you go to the code, and you're like, what is happening? Like, there are so many words, so many things that don't seem to make a lot of sense. So, okay, let's try to get an overview of what is actually happening in this one. First off, I'm going to move the brackets because I don't like new line brackets. Sorry for those of you who do enjoy that. There we go. Why do you choose this over shader graph? Gives you more control. That's pretty much it. I mean, it also depends on what your target render platform is and whatnot. Like shader graph is only for the HDRP, I think. There's no, like, shader graph doesn't allow you to make like standard pipeline shaders and whatnot, right? So it depends on a lot of factors. What are the differences between the types of shaders in Unity? When you select a shader in Unity to create, you kind of select the preset template. It just picks a template for you. So I did the unlit shader template. So this is the template code that it gives you. Okay, I'm gonna start by removing a few things to simplify the process, because not all of this is actually necessary. So we do need that, don't need that, don't need this. Okay, slightly more readable now. We don't really need the property either. Don't need log. Okay. Oh, I actually need to return a value? What do you mean? Let's give this a just a white color. There we go. Okay, so simple shader. So how do we apply this to our object? Well, we need to create a material, right? We talked about this before. So let's go to right click the shader, go to material, and then we got our shader here. And then we can apply this to the object. And you can see that it's actually working. Look, we got an object. So, and this is now rendering using our shader. Our shader is extremely basic right now. It literally just outputs white. Like, it goes through every fragment and then outputs straight up the white color. Okay, so let's go through what these things are. First off, shader, this is the name and path of the shader. So this is when you select a shader for a material, this path right here, it has like subfolders and whatnot. The names here are based on this first line right here. So you can give this whatever name you want, right? So in this case, it's just called simple shader, automatically went into the unlit path because we chose to make an unlit shader. Okay. Properties. Properties is all the stuff that's defined per material. So here's where you can do inputs like color and texture and whatnot, but we're not going to do that yet, so we can just ignore this. Subshader, this is kind of where the actual shader starts. There's a lot of conflicts in terminology of shader, subshader, fragment shader, vertex shader. Like, all of these are shaders, but it's just very confusing. But there's another layer in the other direction if you have like branch compiling based on stuff, and then you have another set of shaders, and then you have a meta shader, and like, yeah, it's confusing. Sorry about that. But anyway, the subshader inside of a shader asset in Unity is the thing that contains the vertex shader and the fragment shader. Okay. So how does this work? CG program. This is an indicator that tells us from here on we start writing CG code, which is the programming language you use for writing shaders in Unity quite often. So you can use like is it GLSL or HLSL? I think it's HLSL to write shaders in Unity, but we're going to do this in CG. So yeah, from here onwards it's CG, and then at the end you have an end CG which ends the actual code. All right, so far so good. So what's all of this? Pragma tells you what Pragma is a pre-compiler step. It's just there to tell you what's the name of the vertex shader and what's the name of the fragment shader. So you can see that there are functions down here, one called vert and one called frag, and those are the names up here. You can see they correspond to each other. This can be anything. We can call it like potato, like this can be called potato, and then we slap in potato there, and this is still valid code. It still works, right? So those are just names. But you need to say, you know, the vertex shader is called potato, fragment shader is called frag, right? Anyway, let's keep the name vert because that's more descriptive. Okay, good. So include. The include here is used for Unity specific functions and macros that are super helpful for structuring your structuring your code and more easily tie into Unity systems like lighting and positioning of objects and all of that stuff. So this kind of just grabs the code inside of Unity CG, literally pastes it in here, like all of the lines from that one during compilation. So this just takes CG code from a file called CG include, and then just like dumps it into your shader. So this is super useful. You can also write your own CG include files in case you want to have like common functionalities between various shaders and whatnot. You can put that in a CG include file and then include that in all of your shaders. You'll see surf sometimes. What is it? Surf is for Unity surface shaders. I actually don't know if they still have surface shaders. Standard surface shader, yeah, they do. Okay. So the surface shader, this is it's kind of a simplified way that you can pipe into Unity's lighting and all of that. If you want to write a custom shader like we're doing in this tutorial, that gets very complicated actually. But if you use a surface shader like this one, then it gets very easy, but you have less control. So it kind of depends on what you're doing. So if you want to tie into Unity's lighting system and light maps and all of that, it's probably best that you do a surface shader. And that one has a single function called surf, because this is kind of Unity's own way of dealing with how to set up a shader here. And then you kind of output different things like, you know, the color of the thing, the metallicness, the roughness or smoothness and stuff like that, right? But yeah, we're not going to do that in this tutorial, but it's called surface shaders in case you want to look into it. Yeah. All right. Delete. There we go. Okay. Now we have a simple shader. How does this work? What do we do? Let's see. We went through to the include one. So the include one includes a bunch of Unity functionality that we are interested in and that we want to use. We actually only use it in one place here, but yeah. Okay, here we go. App data. What is app data? App data here is the actual mesh data. Mesh data. So this is like vertex position. You have like vertex normal. You have your UV coordinates. You have tangents. Like and vertex colors. There we go. So app data is a structure to define what data do you want from the mesh, right? I usually call this vertex inputs because it makes more sense to me because it's the input to the vertex shader, right? So I'm going to rename that to vertex input. And again, we need these names to correspond to each other. So I'm going to put vertex input over there. Okay, so we have our vertex input structure, and here we define what do we want from the mesh. This one is actually very specific with what words you use here after the colon. I think it's called semantics that you need to define explicitly. So these kind of have a very limited set of things you can get from the mesh. But yeah, so if you do want to get like the vertex colors, it's called color, I think, or maybe colors. I think it's color. We'll see. I'm going to get an error if it doesn't work. If you want the UVs, like UV channel 0, that's text chord 0. And if you want UV channel 1, you do text chord 1 and so forth, right? You can kind of see the pattern for the UV. It's just called text chord and then an index for which channel you want to use, right? And usually you do float 2 for UVs. You don't have to, but you can. Usually you can use float 4 if you want to, but that's kind of rare. You tend to not do that. Yeah. let's see, you've got the normal as well. Let's call normal. So yeah, that's almost all of it. There are probably a bunch of extra things you can get as well, like related to skinning and whatnot, but anyway, we're not going to go through that. What are UV channels? So UV channels is the most common use case is that you use that to define 2D coordinates on your 3D mesh. So here's an explanation of UVs. Say you have an object like a sphere, right? So we have our 3D model here. It's a sphere. Then you want to apply texture to this. And then you ask the question, like, how do you apply this texture? Like, do we wrap it around? Do we like project it from one direction? Like, how do we do the actual mapping of the texture here, right? That is usually done through UVs. So most like, 3D applications have a thing called a UV editor. So in here, there's a bunch of triangles, and all of this is like, each little dot here is a UV coordinate. So this is a position of a 2D coordinate for the mesh, and that corresponds to a certain vertex, right? So in this case, let's see, you can see that all of these UVs are at the top here. Like there's a little green dot there. If I go down, you can see that there's an expanding set of rings, right? So these vertices here correspond to these UVs. So for all of these vertices that are green right now, they all have the same Y coordinate in the texture, right? So if we go to Photoshop, for instance, there we go. Let's give it some arrows. This is 0, 0. Then I have 1, 1 here. 0, 1. Wait, yeah. Sorry, think about coordinates. Wait, x1, y0. Perfect. What a texture. Actually, we should also get we should get a texture from the internet. Let's go to the internet. Search for grass. There we go. Grass texture. Hello, grass.
Hello.
I'm glad that grass is here to respond to me. One of them's got a lot of contrast. That's perfect. What a great shader, or its texture. Perfect. We're gonna scale this up because we don't care about shader resolution. Oh yeah, heck, forgot the things. All right, there we go. What a great texture. Let's save this on our desktop. Let's call it texture.psd. What a good asset name. Just call it texture. All right, let's slap it onto this object. File from the desktop. It's called texture. this ad that I got. It's so bad. If you're over 40 and own a computer, this game is a must-have. Fishing game. Sure. All right. Maybe we should have used that texture. Let's see. Oh, we're not displaying textures. There we go. Erotic fishing, best game I've ever seen. Yeah. Okay, there we go. What a great mapping of this texture. So now you can see that we've applied this grass texture to this one. So let's see. Let's analyze this. So how does this UV mapping work? So you can see that it's continuous for the most part, but here there's an interruption. So what is that? That is the seam between where you cut the UVs. So you can see that the what did I do? Let's not do that again. Yeah, so you've got the UVs here, right? And let's move to a different quadrant just for visualization purposes. So you can see that this line right here is where the seam is, and that's because this texture is not tiling, right? But anyway, so what happens if we modify these UVs? Well, what happens is that we move the texture, how it's mapped to this object, right? Because we move the coordinates. Or if we scale the coordinates, we kind of scale the whole texture around, you know, the pivot where we're scaling it from, right? So these are 2D coordinates that are most commonly used for, you know, defining coordinates to map a texture onto your 3D object, right? But yeah, so the data you get in the mesh for the UV coordinates is literally just the coordinate of each of these vertices. So each vertex has a UV coordinate. That UV coordinate is in UV space, as in the space you're seeing right here. So, you know, it's going to be relative to the bottom left corner here. Yeah. Also, mesh can have many UV layouts, one per channel. Yeah, exactly. So as Cookie is mentioning, you can have multiple UV channels. So you can make another UV set, as it's called in Maya. Yeah. Can I have multiple UV coordinates for one vertex? Yes, you can. So this was one. This was UV channel 0. So if I make another UV set, I can go to create, copy UVs to UV set. There we go. Now, no, wait, hold on. I need to select the things. God damn it. How does one select items? Copy UVs into new UV set. There we go. Okay, so now I have a second UV set here. Yeah, there we go. So this depends on your implementation in your shader, right? Are you using a plugin for UVs? If so, what's the name? This is UV Deluxe. Yeah, so now I have like a different set of coordinates, and this current shader in Maya is not reading from these UV coordinates in UV channel 1. But I can like toggle back and forth between these two UVs to change to those coordinates, right? Yeah. Can you move the UV positions about texture in Unity? Yeah, you can move UV positions. So you can manipulate all the data from the mesh in the vertex shader. We're gonna get to that soon as well. Okay. Anyway, so this was a whole bunch of inputs. But for now, I guess we can just like skip all these. And just first, let's just look at the fragment shader, because that's the most straightforward one to look at to begin with. So what did we have here? Think about the file Guilty Ghost. So the fragment shader, as we mentioned before, that one returns a color. The return value of the function is here, as usual in code. And you might see different terminology for this to be used. You can see fixed. You might see float, and you might see half. These are different precisions for the variable that you're giving. Think about the following, Miri. So the one with the highest precision, that's the most accurate one, is float. So usually I just use float for everything. So I just use float for, and that's a 4-component vector. So this is equivalent to vector 4 in Unity, or in C#. Think about the following, Nicosma. But yeah, so the fixed and half precision ones, I think those are still only used for like non-desktop platforms like mobile. I could be wrong. Don't take my word for that. But yeah, so for desktop, I just care about float for the most part. I think Unity has documentation for like the ranges within where these are valid. I think half is like from negative 32,000 to positive 32,000 or something. Fixed is like valid between -1 to 1, and float is like your standard floating point precision, which is negative lots to positive lots. Right, anyway, we're probably just going to use float for this. No, we are actually going to just use float in this tutorial. Do you call it a tutorial? It feels strange to call this a tutorial. I guess it technically is. Oh yeah, I never fully explained all of this. Let's see. We only got here so far. Okay, so we got to the vertex input. That's the data coming from the mesh into the vertex shader. Great. What is this then? This is the output of the vertex shader that goes into the fragment shader. I usually call this vertex output instead of fragment input. Not sure why, but here we are. Lecture masterclass. Thank you, Steve. I'm honored that you call this a masterclass. Okay, so vertex output. I renamed that one, so we need to rename the return value of the vertex shader and the structure right here. Okay. So yeah, the vertex output is what the vertex shader gives to the fragment shader. It's a bit more involved than that, and we're going to get to that in a bit. Okay, and then we have these two. These two are simply variables. Usually, or no, they can be there, I suppose. These variables are usually tied to the properties that you have. So this shader started out with a texture property, and then that one corresponds to this sampler right here. But we're not going to use these right now, so we can just comment those out. There we go. Then I also need to change the input to the fragment shader. There we go. I'm gonna call that O because it's a vertex output. Or no, should I? Should I call it I? I don't know. Let's call it O. Okay. All right. Let's see. Oh, by the way, Ashley, is it colder outside if we open a window or? Okay. Why are there multiple UV channels? The reason is that you sometimes want to map multiple things to 2D coordinates. You can have multiple textures that you want to map to these coordinates that you want to like composite in the shader. So maybe you have one UV channel that is meant to position the texture as usual for, you know, the color of the object. But you might have another UV channel that is used for light map coordinates. So you then apply lighting on top of your thing, right? So using those coordinates. So there are many different reasons why you might want multiple UV channels. You can just use them as coordinates for doing math in shaders too. So it really depends on what your use case is, right? So yeah, it depends on what you're going to use them for. It's basically, so on a higher level, UVs are just data from the mesh. You can give them whatever you want. You can just write numbers into them and then you get numbers out of it, right? It's just that most commonly you tend to use them for texture coordinates, but that's not always the case. Yeah. All right. Hello. Also, by the way, person who's going back and forth occasionally is Kyperia in chat. Hello, Cart. Okay. So, all right, let's see. We're at the actual vertex shader now. So now we're at the actual proper vertex shader function. So here we are. What's happening here? So first we need to define the output structure here. So that's a type, it's a struct, and we have a field in this one called vertex, and then we assign to that one. This one called vertex has a special semantic called SV position. The SV position has a special significance because this is the one that is going to be read as the clip position of the in the shader, right? So technically this is kind of the clip shader position that you need to define in order to position the mesh, where you want to position it within the camera, right? So that's the vertex field here. And you can see that this one is assigned to here using the inputs v.vertex. So the input v.vertex is the input from the shader right here. So yeah, I don't know if this has to be called vertex in the vertex output structure. It might be valid to call it something else. Let's call it clip space position and see if that's gonna work. I think that's gonna work. We might have some other errors. No, this seems to work. Okay. Okay, there we go. So now we have the clip space position, and that's a required output for the vertex shader. And now we have the function in Unity called Unity object to clip position. And then we give it the vertex, the local space vertex from the mesh data, right? Unity handles transformation from the current view matrix and the model matrix and all of that to transform the vertex from local space of the mesh to clip space of the current camera. That's what this line does. That's all we're doing in the vertex shader now. We're not doing any shenanigans in here. It's just straight up, you know, positioning it, right? Okay. You can get errors sometimes if you change the name, because sometimes Unity seems to call vertex or position something for some light functions. Yeah, Unity can be super picky with, like, sometimes they have macros where they assume certain names for certain functions. So the safest way is probably to call this vertex. But for now, let's call it clip space position because it's more pedagogical, right? Because this is literally what it is, right? Okay. All right. Cool. So this is kind of just a pass through. We're just like piping it back, and then that's it. All right. There is actually a shortcut for this. I don't know if I should go through that. Like, you can take a shortcut with this one. Since we're just returning a single value, we can just literally return the clip space position and just skip the whole structure altogether. So now we don't even have that, like, vertex output thing. Now we just have a float for input. That should still work. Let's see, that one. Missing semantic. Yeah, there we go. So you can, like, short circuit that if you want to, if your vertex shader is doing, like, literally nothing else. But we're gonna want to do other things in that one. So let's undo all of that. Vertex output, was there anything else? Yeah, the semantic shouldn't be there. And we want that one back. Okay, are we still up and running? Okay, good. One thing that's weird is you stock the clip space value during the vert function, but when we read from fragfunc, it's lerp. What do you mean by it's lerp? I haven't gone through interpolators and what that is and how that works, passing data between vertex shader and fragment shader. I'm gonna do that very soon. Okay, so we got the fragment shader now. We've gone through the vertex shader. The fragment shader takes an input from the vertex shader. In this case, we don't use this input whatsoever. We're just, like, ignoring this. But yeah, we could use this one if we want to. I actually don't know what this would look like. So let's say we do have a flow3. Let's say we want to get the clip space position inside of our fragment shader. So let's just do that. Grab the clip space position .xyz, because clip space position is a float 4. I'm pretty sure. I could be wrong. There we go. Yeah. So there we go. And then the clip position, we can just, like, output that one in the RGB channel, so the float 4. And then the alpha channel doesn't matter. It's unused in this shader. What does SV target mean? Oh, right. Wait. SV... Oh. SV target? I don't know. This is required for the shader to work. It's probably, like, a lot of these semantics are to guide the compiler and whatnot to make sure that everything's working properly. Wait, I don't need SV target now. Or wait, do I? No, yeah, I need target. I had position before in this thing. Never mind. Sorry, I'm confusing things. But yeah, it's like a semantic, like SV position. It's just like a thing you need to specify things. Yeah, someone can probably give you a better explanation than me. Again, I'm a very pragmatic developer. I learn the things I need to learn to make the things I want to make. Then I tend to not go deeper than that. Okay. Right, so now we have our clip position. Let's see what that looks like. That is very yellow. It gets white very close to the camera, and as we go further away, it's very yellow. Actually, I'm kind of curious. I wonder what happens if we change the... Let's see. What if we change the camera frustum here? So we set the field of view to something lower. This is now partially an experimental stream. Actually, this whole thing is experimental. Then let's change the far clip to something very short. That made 0 difference in the Z buffer thing. Okay, never mind. Anyway, clip position is probably something you are never going to use in the fragment shader. I don't think I've ever needed a use for that, but we're gonna go to other coordinates. I thought that would display a more like striking difference, but it didn't. Anyway, we're back to our basic shader now. Okay. Frag seems to inherit from SV targets, I guess functions and all, I guess. I don't think the colon is an inheritance thing. I'm pretty sure that that's just a markup to like specify what is what. I think it's called a semantic. But yeah. Okay, so now we got this very basic shader. What I want to do with this right now is just we just give it a color. We can set this to whatever we want, and it works, right? But we're not passing any interesting data from the mesh to the fragment shader, so let's do that. So let's start with UVs, because we just talked about this in Maya, right? So we got UV0. So let's pass this through, see what happens. So we have UV0 here now. So this is again the mesh data. This is the input from the mesh into the vertex shader. And then we need to send the UVs to the fragment shader in case we want to use that in the fragment shader. If we want to display the colors of them, for instance, right? So then in order to do that, we need to pass it through. So to pass it through, we need a thing called an interpolator. So interpolators are usually defined in the vertex output, and they use the text card terminology. So this is going to be our UV0. Okay, so we're gonna do float 2 because we don't really have. I don't think this mesh has any 40 UVs. So we got UV0 in the vertex output structure, but we're not passing through yet. And now we just haven't assigned to that variable. So let's do that. So O.UV0 equals V.UV0. So now we're just like taking the UVs from the mesh, passing it through to the vertex output function, and then the vertex output function gets, or the vertex output data gets sent to the fragment shader, and then in the fragment shader we can read from those coordinates that we just sent to it. So now we can actually get the UV coordinates here. So we can do UV equals O.UV0. So now we get the UVs from the vertex output here, and it was assigned here, so it all gets interpolated properly, and then we get that data, right? And then if we want to display that, we can just throw that into the color here. So X and Y is now going to be the UV coordinates. So if we go to Unity, you can now see these pretty colors. It looks like a mango flavored thing. Yeah, so what we're seeing here is the 2D UV coordinates that we were talking about in Maya, right? So all of these coordinates, where X is the red channel and Y is the green channel of the color output of this shader. So as you can see, this, yeah, you can see kind of how this one is mapped now because of that. So for instance, one thing you can do in the shader, so let's say we just want to see one channel of this. We can do uv.x. So now we've got just the x-axis or the x position of each vertex here. So now this is the x coordinate of all the UVs, and you can see that it goes from 0 all the way to 1 here. So judging from this, you can see that it's kind of a cylindrically mapped thing, right? And then let's look at the y coordinates. And here you can see that it's 0 at the bottom, then it goes up towards 1 over here, right? All right, so now we're actually able to visualize data from the mesh itself, and this can be super useful. Okay, did that make sense so far? I'm gonna explain interpolators in more detail soon. Like why they're called that is probably reasonable. Okay, so let's see, I probably should recompile that one. Go away, camera. Perfect. All right. One person considers this to be perfect. Great. Then this is perfect. Great. Okay. Let's do another one just for clarity. Let's do another thing that we want to send from the mesh to the fragment shader. Let's do the normals. Think about the following parallel jump. So the normal is is the normal direction of each vertex. So usually called the vertex normals. So you can, this is commonly used in shading. So if we, for instance, remove that one and then make another sphere, you can see that the shading in Maya, it depends on the direction that the surface is facing, right? And that data is defined in normals, where each vertex has a direction that is pointing in, you know, whatever direction you specified in the mesh, right? Usually there are two common ways to set things up in models. You generally have either smooth normals, in which case the you can see that there are no like hard edges. It's just like a smooth surface. There are no like discontinuities anywhere. But if you want to, you can make a hard edge like this, and now you do have a discontinuity because now the normals are pointing in different directions there. So yeah. Yeah, if you have like a harsh thing like this, you usually want to have a hard edge here in case it's like an intentional intentional shape of whatever the thing is you're making, right? Like if I do this, I probably want to have a hard edge here and not a soft edge, because if I do make a soft edge, it looks kind of wonky in case I wanted it to look like a cut-off sphere, right? So yeah, the difference between these two states is how you how the normals are defined and how they're split in vertices, but that's more advanced, I suppose. I don't need to go into the details of that. I can show the normals. So I think that's here. Vertex normals, there we go. So now you can see the normal of each vertex on this one. So there's like a green line pointing out from every vertex of every vertex of this mesh, right? And you got this hard edge has two normals. One is pointing out to the left here, and one is pointing straight up. And that's because these belong to different triangles. So these two triangles have a vertex here where the normal's pointing up, or I guess these aren't triangles in this case, but they would be triangles. And then these two have a vertex here where the normal's pointing in this direction. And quite importantly, something you need to note is that technically there are now multiple vertices in this corner, because the vertices can't have multiple normals. Each vertex internally only has a single normal. So when we go through the vertex shader is going to run twice here on this vertex right here, because we have two different states here. So one vertex can have multiple normals, so there's not the same vertex but at the same position. It's a different vertex. There are multiple vertices here now, not just a single one. Yeah, I just mentioned that. Stream delay is a thing as well. So, but yeah, did that make sense? Okay. So let's say you want to visualize that. So let's go to Unity. So now we have the normals here. It knows that it's supposed to grab the normals from the mesh because of this semantic right here, because we tell it to do the normal. The name of this one can be anything, the same with all of these. Maybe not this one, I'm not sure. But yeah, the important part is the semantics here. Cool, so we got the normal. Now we need to pass this through the vertex shader. And we also need to have a slot for that and the output data of the vertex shader, right? So the normal is going to have an interpolator here now. So we add an interpolator. So let's call this normal. And that's going to be the next interpolator, which is TextCord1. And then we have normal here, and then we need to now we're going to pass this through the vertex shader. Again, we're not going to modify this data. We're just going to like send it through, and then that's it. So we're going to do o.normal equals v.normal again, because this is just another pass through, right? Do you have to normalize interpolated normals in the frag shader? That depends. That depends on what you're going to use it for. I'm going to go through interpolation very shortly, because the normal is a very, very good use case for why it's important to understand how the interpolation works and why they're interpolators. Yeah. Okay, so now we're just passing through the normals. Let's see, v.normal is correct, o.normal is correct. Great, okay, so now we have the normals here. Let's just grab the normals. Normals. And then O dot normal. Was it normal or normals? Normal. Okay. Let's do normal. So much normal here. Okay, so now we're just gonna output the normal. And let's see what that looks like. That is not Unity. There we go. So now we're visualizing the normals. How can we tell that it works? Well, you can look at the axis or the gizmo, right? The gizmo in Unity has the three colors. We have red, green, and blue. So if you use the left hand in Unity, then you can have RGB, X, Y, Z are connected. So you have your gizmo. It's kind of like hold on. There we go. You have a gizmo, and then you have RGB and XYZ, and that's your pivot point, right? So you kind of have that connection between like color and coordinates, right? So yeah, that's how these coordinates are related. So if you have a normal pointing upwards, that's going to be this vector right here, which is the green vector, and the components of that one, this vector right here, the y vector is 0, 1, 0. As a color, that would be green. So these things are tied together. So what you can see here is that it's green at the top, which means the normal is pointing upwards. It's red on this side, which means that it's pointing along the x-axis. It's blue here because it's pointing along the z-axis, right? Okay. Is that normal text card 1? Is it correct? Shouldn't it be normal? So it's kind of a confusing terminology thing where in the vertex input or the mesh data, text card specifically refers to UVs. But in the vertex output, you just have interpolators, which use the same terms, which is kind of confusing. Like I would have preferred this was called like interpolator 0, 1, 2, and so forth. But anyway, oh, sorry, heck. Thank you, false bracket. Right, so in the mesh data, these semantics have very specific terms. Text card 0 refers specifically to UVs, whereas in vertex output, this is going to be interpolators, and they're always called text card 0, text card 1, and so forth, with the exception of SV position, because that's a special case. But yeah. I think you might be able to name the normal and color in some cases. I've seen that and I'm not entirely sure how that's set up, but anyway. Actually, let's see if it works. I'm curious now. Yeah, that does work. Well, let's do it. But I'm pretty sure internally that's just another interpolator. So I think I usually just use the interpolator terminology because, why not? Okay, super. So we got normals. What can we do with this? So what's the point? Why do we need the normals? Why do we need this vector? What's the fun in this? There's a lot of stuff you can do here. Why is my sphere black at some surface? That could be a number of factors. I'm not sure. I don't think I can debug your shader live. You probably have an error somewhere, or actually none of it's black. In that case, I'm not sure. There could be like a platform thing where like your Unity is set to the wrong platform that is just up as black because it's not supported or something. Sometimes I've seen some interpolators use an internal data command. How does that work? I don't remember. I also remember that there are a lot of macros in Unity where you do like Unity fog coordinates or something, and then you have like 2 and 3. This is a macro that Unity has defined in order to be able to like to have Unity write code for you that is tied to the way that their fog works, and then you need to supply the interpolator index to the function. In this case, it would be text card 2 and text card 3, right? Yeah, so it could be a macro. It might be like, it could be like instancing macros and stuff. I'm not entirely sure which one the internal data is, but yeah. Yeah. Oh yeah, also as Kyperia is mentioning, there's the opposite side would just be pitch black because all the components of the vector are below 0 here in this quadrant. Is it quadrant if it's 3D?
Octants?
Octants? That makes sense. Yeah. Yeah. Oh, that's it. I have this. All right, super. Also, thank you, Ashley, for answering the thing. Okay, cool. We got normals. What do we want to do with this? So I can go either of two ways. Think about the follow. Why is the opposite side not white? Because the vector is normalized. So the length of the vector is always 1. So when you get to the coordinate right here, which is all of the axes are all x, y, and z all have a positive value, and they're all pointing diagonally in this direction. But it doesn't go to 1 because the length of that vector has to be 1, because they're normalized, because the vectors are normalized, if that makes sense. So it's grayscale along that axis, because all the 3 components are the same, but it doesn't go fully white because it doesn't go all that way. Okay, so let's see if we can manipulate this, just to show you how you can use math to remap this data or something. So okay, we do have the normals. Let's say we want to have a bit of a different way of showing this. Let's say we don't like the fact that there's the z component goes to 0 all across this hemisphere. It's kind of wasted. So say we want to visualize the whole range of colors, right? Then we can remap this range. So because these normals are from -1 to 1, so we want to change this so that they're between 0 to 1. So if you want to do that, it's pretty straightforward. So the full distance of this is 2, but we need the full distance to be 1. So let's divide it by 2 first. So by dividing it by 2, it's now between -0.5 and positive 0.5. But if we divide by 2 and then add 0.5, we're now going to have a range between 0 to 1. Yeah, actually, we should probably multiply by 0.5 instead. So there we go. So now we kind of remap this range, and now we get this more normal map looking thing. So if I look from this direction, you probably recognize the colors here. That's because in normal maps, you can't have negative values. So normal maps remap it to 0 to 1. And then when you unpack it in the shader, you push it out to -1 to 1 again. So now we just did kind of the reverse. Yeah, so for instance, I could literally take a screenshot of this now and then use this as a normal map in a shader in case I want to. Is the last value in the return statement of the frag function the alpha value? Yeah. So I'm just constructing a float 4 here, which is a vector 4 if you're familiar with C# or coding in Unity. So yeah, this is just the alpha channel. So now the normal is in RGB because this is a float 3, and the alpha channel is currently 0. Yeah, but this shader doesn't use the alpha value. It's important to note that alpha is not the same thing as opacity. So it kind of depends on how you set up your shader, right? Think about the follow. Yeah. So okay, so we can do all sorts of math to manipulate this and visualize it the way we want. And yeah, so this is kind of this is kind of the way you start manipulating values to get the output that you want, right? All right. So let's actually use this to do some shading, which is, I guess, where the term shaders come from. So let's go back to having the normal that is not remapped to this weird range. So now we have the actual real normals of this one. Okay, so let's do some basic lighting. Let's hard code some lighting into this one. Let's say we have a light direction. So we need a direction to a light source. Let's call it light direction. I'm gonna hard code this into this shader now. So this is not how you do actual lighting. I'm just kind of piping in hard-coded light direction just so we can do the math for setting up lighting. Okay, let's just give it a vector that's coming up from the diagonal that we had for the normals, right? Think about the follow, Cole. Okay, so now we got the light direction. Here we go. Hello, Ziska. I don't know how late you are. It depends on what you wanted to catch. This is going to be uploaded to YouTube afterwards, so you can catch it there too in case you missed stuff. Also, welcome to the stream. All right, this is going to be our light direction. We also need to normalize this one, and shaders have a built-in function called normalize, so you can just do that, and then it's going to make sure that these the length of this vector is 1. What else? We might want a light color. I suppose we can do that later. We don't have to do that now. Cool, so now I have a light direction. So now that we have a light direction and a normal, we can start doing some lighting math. All right, so there's a specific function, or lighting function that's called Lambert lighting, which is basically just someone who managed to slap their name onto the dot product within shaders. But let's sketch out what a dot product is, because I'm guessing a lot of you who haven't gotten into shaders are intimidated by it because of math. So I feel like I should explain a few concepts that are very important. All right, so dot product. What is the dot product? How does it work? It's a very, very simple function. I could go through how it works mathematically, but that's not really relevant. So let's just do the vector interpretation of this. So we talked about the fact that we had the normals of the mesh, right? You had your vertices, and then you have the triangles in between them, and then each vertex has a normal that's pointing out from the surface. So this one is pointing out here, this one is pointing out here, and so forth, right? So one thing that's common amongst normals in general is that they have a length of 1, right? So this distance right here is 1, and that's called a normalized vector. So that means that any normal in a given coordinate system is always going to lie in a circle around here, because they always have a length of 1. Why does that matter? Because there's a very nice property of a function called the dot product, where if you have two normalized vectors, say you have the normal vector and the direction towards the nearest light source, let's say you have that, then these two vectors running an operation called a dot product on these two is going to be a very nice approximation of a diffuse lighting bouncing off of the surface right here. So let's see. So how does that work? So what happens is that if you have a vector like this, and you do the dot product between these two vectors, what it's going to give you is the value right here. So this distance. So this is the result of the dot product. So you do dot of, let's say we have A and B. Let's do capital letters. A, B. Dot product of A and B here equals whatever you have here. So that would be something like, I don't know, 0.7 or whatever. So what happens if we keep modifying this vector? Well, you do get a very nice gradient. So what does that look like? So let's say we move this arrow. So instead of it pointing this direction, let's have it be a really low angle. Then the value is going to be even lower. So what happens is that arrows that are very close to each other, like this, so you have the normal here and the light direction here, because you have a light source somewhere. These two are going to be very close to 1. And the ones that are pointing very closely away from it, like this, these are... thank you so much for the thing. Yeah, so these two, the dot product between these two, are going to be very close to 0. So what's going to happen is that you have all of these different vectors, and the values you get as you go around this circle is that it's going to be, if they point in the same direction, the output of the dot product is 1. If they're completely perpendicular, the output is 0. If they're completely opposite, the output is -1. And it goes the same thing in the other direction, 0 here, and so forth. And then you get all the values in between. So it's not a perfectly angular one. So this one, for instance, is not going to be 0.5. This one's going to be a bit higher, like 0.707 something. So and so forth. But you're still going to get the gradient. You're going to have, you know, 0.9 something here. You're going to have something lower here like 0.4 and so forth. So what you get is a value that goes from 1, and then as you angle over here, it gets lower and lower and lower. So this is super useful to have a value for how similar two normalized vectors are. That's kind of a very high level view of the dot product. If they're extremely dissimilar, as in pointing in the complete opposite direction, you get -1. If they're completely the same direction, you get 1. If they're completely perpendicular, you get 0. So that's kind of a nice way to interpret the dot product and why it's useful. So let's go to the shader and see how we can use the dot products. So now we have a light direction. We kind of just said that we're gonna have a light position at, you know, normalized direction towards here, which in 2D would just be, you know, we have a coordinate system, we have 0 here, and then we have a light position. In our case, if we have the x-axis and the y-axis, we just set it at 1, 1, which is, you know, in the unit squares is going to be in the corner, and then the direction to that one. So that's our light source right there. Okay. All right, so we have the light direction, and again, we have to normalize that one because it's a direction. We want the vector to be normalized. Okay, so let's just do the dot product between those two. So we do the dot product between the light direction and the normal. Celeste music. Celeste is a fantastic game with fantastic music. Very much recommended. Okay, so what we got now is this is no longer the normal. This is the result of the dot product. So this is like simple light or something. Okay, so, and again, dot product outputs a float because it's like a distance value, right? So even though we pass into 3D vectors, we just get a distance out of it, so that's a float. And then we want to output this to RGB, so we just do simple light.xxx, which gives us, you know, the one component we have in simple light in all 3 RGB channels. All right. Is there a way to debug.log with shaders? No. What I usually do is, like, if I need to debug the UVs, I just return, you know, the UVs themselves to debug. So I just do UV and like that. This is what I usually do to debug. I just return whatever values I got, and then double check in the in Unity. It's like, oh, okay, the UVs seem to work fine, so we're good, and so forth. Yeah. What do you mean by x-axis and it's usually xyz? It's because simple light doesn't have a y and a z component. This is just a float value. I could also just do return simple light like this. But it's just because simple light just doesn't have it's just a single value, right? Yeah. Okay. All right, so let's do the thing. Let's remove our debug output. And then let's see how this looks. So here we go. We have something that looks like it's lit by some light source, right? So you can see that it kind of looks like the light source is up here, right? It's shining from this direction, and then we get this nice little gradient, and then it's pitch black on the backside of it, right? So this is a very, very basic lighting setup that you can use for diffuse lighting, because there's no like shininess to this. It's completely diffuse. The direction you're viewing from doesn't matter in the way that in the color that it outputs, right? So yeah, this is a very, very basic Lambert shading, or actually it's not Lambert yet because we need to do a few more things. So let's add something more to this. Let's add a light color. So light color, again, everything is just float 3 for both color and vectors, or float 4, I suppose. So let's give it a color. So, well, what color do we want for this? Should we go for something like vaguely realistic? Okay, there we go. That's a light color. Good. Okay. Well, speaking about lighting, how do you decide what lighting setup you will use along with the shader? Depends on a bunch of factors. It's like, yeah, like do you want a cheap lighting function? Do you want to unify your lighting across all shaders? Do you want special lighting just for this object? It really depends on what like how your game is set up. So it's difficult to like have a simple answer to that question. Okay, so we got a light color now. What else do we want to do for this? Is it common to implement your own? In Unity, probably not. I think most people use Unity's lighting. But I mean, outside of Unity, in like, I mean, in proprietary engines, then yeah, definitely. But that's kind of because you have to. Okay, so we've got a light color now. So how do we like combine these two things? So we do have the simple light here. It's a value between 1 to 0 for how much the light is shining onto this thing. So what we can do is that we can simply multiply these two values. Because if we multiply something by 1, you get the same output. So if we take a color, multiply by 1, we get the same color out. If we start moving across this gradient, if we multiply color by 0.5, it's going to be darkened by, you know, half of the whole thing, right? And then finally towards this edge here, it gets to 0. So what we can do is simply multiply these two together. So this is our, let's call it light fall off. And then we do light color multiplied by light fall off. And then you go back here and then recompile, and now you see that this actually has a color. It's a bit too red, I noticed. So let's bump up this one a little bit. There we go. That's a terrible yellow. What am I doing? That's a bit more warm. Okay, so now I have something that kind of vaguely resemble a, you know, light coming from a light source, right? In your opinion, is programming a shader a technical or rather creative task? I think in most cases, if you're programming a shader rather than creating in a node editor, it is mostly a technical task, but it should be more of a creative task. I'm kind of the opinion that coding shaders by hand is sort of a means to an end and a necessity rather than something that you should strive for. So like, if you're using a node-based editor, you kind of focus on the art more than the code. But then if you go into like more low-level stuff and like very tightly optimized games, then it is a very technical thing because you need to like pack all the data in a very like tight amount of space because you don't have a lot of memory on like consoles and whatnot. Yeah, so it depends on what shader you're making, but it's something that should be more creative than it often is, unfortunately. Yeah. Okay. Super. We now have something that is usually called Lambert lighting. There's one more thing though that might be difficult to catch. So let's modify this a little bit. Let's give this an ambient light. Just a base light coming from all direction. Just give it some light, right? So for that, let's temporarily remove these for now so we can see how this is all put together. Let's move this up here. So this is a diffuse light. There's like, it's lighting, but it's not view direction dependent, right? So it's just completely diffuse. So let's call that diffuse light as the combination of these. Let's just keep these for the diffuse light. Okay, now we need ambient light. So how do we define that? Usually, it's just a simple color that you add to the whole thing, right? So let's give it some color. Ambient light is kind of usually if you simplify it a lot, it's a sum of all the colors around you, right? Hello, Thor. How are you doing? There's a cat here. Anyway, so it's usually the combination of all the colors around you. So if it's just a simple color like this, usually blue, because skies are generally bluish. But yeah. How are you doing? I'm doing good. How are you doing, Zandy? Okay, let's do a very vague bluish type of thing. So it's going to be slightly more blue than anything else. Let's add a bit of cyan to that. Now we got ambient light. Let's just straight out output the ambient light. See what that looks like. I did an error. Unexpected token flow 3. Right, we need a semicolon. There we go. All right, this one is not fully black, so this now has some ambient light. I think it's a bit too dark, so let's brighten it up a bit. Okay, this is not blue enough. I'm sorry for fiddling around a lot with this. Okay, here we have a very cyan ambient light. So let's pretend this is just like color coming in from all directions. Cool. Now it's lit from all those directions. So how do we combine all of this now? So what we need to do is that we need to sum the diffuse light and the ambient light, right? So we just do ambient light plus diffuse light, and now I have the combination of the light coming from the from our fake light source and the ambient light. But you might notice that something happened here. So this one now goes to pitch black, even though we have ambient light that's coming from all directions. So why is that? Well, if we go back to the dot product, remember that values that point away are going to be negative, right? So what happens is that we're going to get negative values throughout this range right here. So all of these points on the sphere are going to be negative. So what happens is that it's actually subtracting from the light. So the opposite side of our fake light source is removing light, which is not how light works generally. So what you want to do is that you want to limit the dot product so that it doesn't go outside of 0 to 1, right? So there are several ways of doing that. There's a function called saturate. For some reason, it's the worst name for function ever. But saturate basically clamps between 0 to 1. Any values below 0 is going to be 0. Any values above 1 is going to be 1. You can do that. If you just want to clamp the bottom, but you want to keep the upper side of things, you can do max between 0 and that value. So of the dot product and 0, it's going to grab the largest of the two, right? So if the dot product is below 0, 0 is, greater than 1, right? So this is a very common way to make sure that you remove all the negative values, right? Okay, so recompile now, you can see that we have a much more lighting-like solution, right? The ambient light is still being applied to the backside now. It's not being subtracted by the negative light on the other side, right? Yeah, and then you still have the light source working and everything, right? Okay. Does this make sense so far? And am I going in the right direction? Is this what you want to know? Am I talking about the things you want me to talk about? Well, what are your thoughts? I can just keep going, but I just want to make sure that I get cover the things that you want me to cover. This is amazing, Caps. Okay, thank you. Good. I'm glad. Practical examples are the bestest. Gotcha. Okay. Do we want to continue going on doing more lighting, or do we want to? I don't want to continue with lighting, or should I go to explaining what interpolators are? Because I didn't fully explore that. How would you be able to change the gradient so that it darkens the opposite side but doesn't turn to black? Darkens the opposite side but doesn't turn to black. Not sure what you mean. You could just clamp it in a different way or remap those values. Just want to say I was having a bad day and you're saving it. Thank you. Oh, thank you so much. I'm so glad, Outfrost. I'm sorry you had a bad day. Okay, great. Can the gradient be more nice looking? Definitely. This is kind of the level 0 shading. This is Lambert shading, and it's the most basic type of shading. Yeah. How do you apply shadows from other objects? Is that complex? Yes, that is complex. So we're not going to go through that in this tutorial. How do we proceed if we wanted to use an actual light source? Yeah, that's a good next step. Let's do that actually. Okay, to do that, we need Okay, so right now we have a fake light direction and we have a fake light color, right? Like these two are not from the scene at all, right? So level 0, more like level 2. Level 0 is flat color. Well, okay, level 0 flat color is not lighting, I would argue. Well, I guess the ambient light would be. Anyway, I suppose. Okay, let's do the actual light source. So to get the actual light source, I don't remember which one, if we need the lighting.cg or auto light. One of them, probably lighting. And then the next step is to Google for Unity light direction or light color shader, because I never memorize these. Built-in shader variables. Hello. Lighting, here we go. Light color 0, world space light position 0. Perfect. Okay, so there's a Unity variable that's included in lighting.cginc, and then we can now access that one. So we have light color 0, so let's try using that one first. Let's pass that one into, I guess RGB, into the light color, and let's see if we can get that to work. So now if we go to our scene, we have our directional light, we can set the light color, and yeah, so that's working. So now we're actually reading the first light source in the pass of this shader that we have, the one pass, I suppose. We haven't gone through passes. I don't know if we're going to do that, but yeah, so now it's actually using the color from the directional light in the scene, right? Of note here, there's no support for multiple light sources right now. That's a bit of a different concept. That gets complicated pretty quickly. But yeah, so right now we're reading off of this one, but we're not reading the direction. So I rotate this one, nothing's happening, right? Okay, so how do we get the direction to the light source? There's a bit of a special case for if you go to the Unity docs and read world space light position 0. For directional lights, the direction is in XYZ. For point lights or spotlights, the world space position's there. So it's a bit of a confusing name. So yeah, world space light pos 0 for directional lights is a direction. So we can actually get that one with light direction through this one, XYZ. So that should do. Let's see, world space direction. Yeah, so that's the direction it's pointing. There we go. All right, so now if we move this around, rotate this, you can see that it follows along. So I think I don't like the default Unity background. Where's the rendering? Lighting settings. Skybox. Nope. Do you know of a good way to do an arbitrarily sized Gaussian blur in the GPU? Arbitrarily sized is difficult. So that gets tricky. Usually the easiest way is to just not make it arbitrarily sized. You might be able to interpolate with a lower resolution kernel, and then just scale it, but I'm not sure how that would work. Yeah, I don't know. I don't have a good answer for that. The arbitrariness of it makes it difficult, right? Okay. Is there a way to break up blur into multiple passes? You could do separable Gaussian blur. If you want. If you Google that, you'll find resources, but that's a bit too like advanced for the stream. All right, super. So now we're actually reading the light source in the scene. So now we can use this one to do all of our stuff. Oh, I think I have a good path for this. We're gonna do a bit more lighting, and then after that, we're gonna look at interpolators, because there's a very common problem when doing lighting where how interpolators work is very, very important. Okay, did this make sense so far? Or is there anything that was unclear? Let's do a grayscale ambient light just to not confuse the colors of everything. So far so good. Gotcha. Very clear. All right. Good. Okay, next step. Ambient light and diffuse light can be above 1. Yes, that is true. There's, I don't know how deeply I should get into this, but yeah, ambient light plus the diffuse light can go above 1. That depends on, you know, the intensity of the light source you've got, and a lot of factors like that. There's actually a very dealing with the problem of color ranges of like intensity ranges of what value of these pixels is fully white on my screen and what value is fully black. I guess fully black is obvious, but so yeah, there's a lot of stuff that we use in games to handle that, and that is tone mapping and HDR. So what that means in a very basic way is that let's see. Okay, so if you take a photograph of your computer monitor and you want to show that to some friends, so you take a picture of your screen or whatever, take a picture of something inside of your apartment, and let's say you have a vase and the vase is white. So let's say you have this picture. There's a vase of some sort. Okay, so this one is white. So how does that work on the camera? Well, the camera has an exposure value, right? That says how sensitive should these light sensors be. So then let's say it's dark in the background. We want the brightness of these pixels to be at like, let's say we have a range from 0 to 1. Then we want these to be kind of dark, like 0.01 or something. And then the vase, we want that to be 1, because that's like kind of the brightest spot, like the very brightest spot of the vase. We want that to be 1, and then it's going to like be slightly darker along the edges of it, because even though it's fully white, it's still shaded, right? Because you have lighting in your room and whatnot. Okay, that's all well and good. You have your picture, you have your color range thing, you send the picture to a friend, everything looks fine, right? So then the question is, do these values correspond to the intensity of the actual light in the scene? And the answer is no, because if you imagine the light sources you had in this scene where you took a picture of the vase, right? If you imagine that, but you're outdoors in direct sunlight, that sunlight is way stronger than whatever light bulbs you have in your apartment, right? So what a camera does is that it adjusts its exposure to make sure that, okay, we have a lot of light now, so we need to make sure that we don't like go above the range of 0 to 1, right? So then it like clamps or like pushes those values down. So there's like a slope of light intensity of like no intensity, very high intensity. So up here you have like sunlight, and then you might have a, you know, a light bulb or something around this point here. So then the question is like, okay, if we take a picture, what range do we want 0 to 1 to be in? If it's an indoor picture, well, then you might want to have this range right here, because we don't want it to be super dark. If our maximum is sunlight, then these pixels are going to be like 0.5, even though that's a very strong highlight on the vase that you took a picture of, right? So the solving this problem is what you tend to use HDR and tone mapping for. HDR is high dynamic range. So what you usually do in video games is that you render all of your scenes in actual proper, you know, values that go beyond 0 to 1, because shaders can handle that. They can work with values outside of 0 to 1, but your monitor cannot. Your monitor has to have a value between 0 to 1. So generally what happens in games that have HDR and tone mapping is that everything is rendered with like actual values, but if you are indoors, this window of the range of 0 to 1 has to change depending on the situation. So if you are outdoors, this window will move, like if you're from indoors and going outdoors, this window will grow like this, which kind of simulating lowering the exposure of the camera, where this one is like moving upwards. And that's usually done with a tone mapper, which kind of detects the overall light of the scene and then remaps that value back to LDR, which is low dynamic range of 0 to 1 values within your monitor. Or I guess technically it's like 0 to 255 or whatever, but you get the point, right? Yeah. That was a tangent. Anyway. What was the original question? I'm sorry. I totally lost track of the original question. Hold on. Oh, someone just asks if it can be above 1. Right, yeah. Anyway, it just depends on how you set up your lights. Can your light source go above 1? Well, then a lot of things are going to be above 1. Do you want that to be between 0 to 1? Then you need to like remap those values. Yeah. Okay. All right, let's do some more fancy shading. Let's do a specular highlight. Let's do some shiny objects. Or wait, actually, let's get some properties in here. There's a cat. See the tone mapping here? Like Thor is like completely black. So if the focus of this stream was like on Thor, then we would need to like remap these values. I need to increase the exposure of the webcam, right? Because Thor is barely visible. But then I would be like overblown because I would be too bright. Anyway. Yeah, there we go. Real life example. I managed to tangle my headphones. Giving out free muse, yeah. Ashley is currently giving pets. Pat McAllister, thank you so much for the donation. Please make this a regular thing. I might do that, yeah. People seem to really appreciate this. I'm not sure how much I could explain though. I don't know, maybe. Yeah, I mean, I'll consider it. I'll probably do more of this. But then again, the streams that I usually do, I try to keep them educational and I always answer questions in chat. So this is kind of what I'm always doing, but although I work on my own projects instead of like specifically making a tutorial. But yeah. Where were we? Oh, where we gonna do properties, right. So let's say we now want to be able to control the color of this object, because right now it doesn't really have a color. It's just whatever, it's just purely white, right? Because it gets whatever color we're lighting this with. So let's add a property to this. So properties, again, these are the ones that are defined in the material, where you can like assign specific colors and whatnot to your specific things, right? Okay, so all right, so let's define a color. So there's a syntax for how you set up all the properties. You can just search for Unity shader properties. I think I just started learning all of these like offhand, like very recently, because like remembering the syntax for all of this is like messy. Also, thank you, Sandy. Okay, so first off is the name of the property. Second off is the display name, like the property that people see and like assigned to in the inspector. So this is the like color of the surface. And then we need to specify what type this is, so it's a color. And then we need to give it a default value. So let's make it just fully white, because that means that it doesn't affect the light at all. So it's a good default to have, I think. Thank you for the follow. Regengel? Yeah, that. Cool. Okay, now I have a property. Let's now use this property in the shader. So let's just debug output that one. But first off, we need to define that variable here. So it's a float 4 because colors are RGBA. So we just specified here. So float 4 color, that's it to kind of tie it to the property. So make sure that this name matches this one. And then we can just return this value. So now we're just skipping all the lighting. We just immediately return the color in this shader. So now if we look at the shader, there's now a color property at the top. Also, I guess I should make the alpha 1 on this one in case we add transparency to this. Okay, so now we have a color that we can control per shader. So if I duplicate this one, make another material, and then give this a different color, these two are now using the same shader, but they have different colors because the materials have different inputs, right? So let's make one more. Let's assign that. Yeah. There we go. Okay, good. So let's go back to our shader. Let's see how we apply lighting to this now. So there we go. So now they're all completely white. They all just get the color from the light source and that's it. And that's not what we want to do. We want the surface color to still be part of this lighting function, right? So let's see this. Let's see how we structure this now. We have the light direction, the light color. So these are related to this. The final output, this one, this is the direct light coming from the light source, right? Because this doesn't include the ambient light that we had before. So let's call it direct diffuse light. Let's comment a few things. Lighting, there we go. So direct diffuse light and then we have ambient light. Combining those two is what we did here, right? So let's give this a name too. So this would be our diffuse light, kind of the total contribution of all the diffuse lights that we have, right? Okay, and then we need the color of the surface, but affected by the light, right? And that's simply a multiply. So we do diffuse light multiplied by the color, right? Which is underscore color. And we also want just RGB. And that's our diffuse light. I don't see how you can change color for the same material. When I change color, I change for every object. You use multiple materials. There are different ways of doing that, but multiple materials is one way of doing it, yeah. All right, so what we got now is that we combined all of our lighting contribution, which is direct light and ambient light. So direct light, and then here we have ambient light. And then here we composite the light into a single lighting thing, right? Or, well, we composite everything, right? So we have the diffuse here. So this is a composite. And then we apply, or then we multiply the color by the diffuse light. So if we go back to Unity now, we have a compiler error because I redefined diffuse light here because I did not finish this whole thing. So we need to remove that one because we tried to define it twice. Are there any shortcuts other than creating a new material for every slight variation of an object? It depends on what you want to vary it by and whether or not you want that variation to be an asset that you can apply yourself. So it depends. You can also do like per instance stuff that like through code with property blocks. So you can do like, yeah, there's a function in like renderers. We can do set property block and that one has a specific setup for properties. That's per instance. So you can do that. So if you search for material property block in Unity, you'll find it. Let's see if this compiles. It does not. Right, I do diffuse light there. This is now called direct diffuse lights. There we go. So ambient light, direct diffuse light are combined into the total diffuse light, which we then multiply by color. So this is actually the final surface color, right? And then that's the output we want there, right? Sorry, I'm like trying to speed ahead of myself all the time. So there we go. Look at these very diffuse spheres. How do you like the diffuse spheres? So now we made a super basic shader. You can specify the color of the surface. The color of the light source is still going to affect this. So if we give that a color, it's still going to be working as you'd expect lighting to work, right? But yeah, usually it's kind of close to white, but yeah. Okay. How does Unity allow you to use a single material sprite and use a different texture for each object without needing to create a bunch of sprite materials? That is also done using property blocks. So material property blocks is the solution for that. You can kind of do per instance data without using material assets using material property block. So if you go to like Unity material property block, here you go. This is the thing you want to use, material property block. There you go. We're not going to do that for this tutorial because we're not doing it in C#, I think. Okay. How does this does that make sense so far? Does the whole lighting setup for all of these things? I'm guessing we're fine. I'm guessing we're ready to move on to doing specular lighting because now it's all diffuse. Like the view direction doesn't matter anywhere here. Okay. Let's do specular lighting. I think we're ready. Okay, this thing is growing now, so it's gonna get more and more complex. So let me know if there's anything that's unclear with this, because we're gonna keep working on this one. Races, thank you for the follow. Oh, also, whoever donated before, you donated $10, which means I should send you a Steam key for Flowstorm, the game that I'm working on stream. Yeah, I should send that to you. I'm gonna do that after the stream because I'm in the middle of all of this stuff. So yeah, thank you so much for the support. Yeah. Okay, let's do specular lighting. Okay, so now we have the direct light, but this is only direct diffuse light. So now we need direct specular light. So let's see. If we so if we want to do specular light, that is like reflections off of the object, and reflections are view direction dependent. That's why like shiny objects that are like have like, I don't know, like crystals or whatever that are very shiny, they look very sparkly because as soon as you move your head, like the shading changes on them, right? And they're very like reflective. And that's specular light. The diffuse light doesn't like change, you know, the color of a specific point on the surface. At least not with this lighting model, because this is a very basic lighting model. If you want to get into like physically based shaders, then it does matter. But in this case, it doesn't really. So we're doing a very basic setup now. Okay, so for the specular light, we need the direction towards the or the view direction, which is kind of the direction from the surface to the current eye. Now I'm talking in VR terms, to the camera. So we need to define the view vector. For that, we need the position of the camera, which can be accessed through a thing called the World Space Camera Pos. So let's go here, and then let's define all of the things we need. So float3, camera position, world space camera position, and now, did you say you work on Flotsam? No, I work on Flowstorm, which is the name of my game. Okay, we have the camera position, but then we need one more thing. We need the position of the fragment being rendered right now, and that we don't have. There's nothing here that can help us, you know, to figure out the position of the actual fragment that we got. Very gratifying to see how much you're Googling, because I literally never remember the names of any of these things. No, like, you don't have to remember them, so why remember them? It's just useless. Like, yeah. Do you have a link? I actually don't really have a proper website for Flowstorm. I do stream Flowstorm. It's pretty much every time I stream here. But there's information below the stream. And I mean, I can show you the game if you want to, but I'm guessing most of you are here for the shader stuff. So yeah, I mean, I can show you how I've used shaders in Flowstorm in case that's useful. But maybe I should do that later. It's up to you. Like, it's up to you. Like, whatever all of you want to do. So yeah. Okay. Right. We needed the current fragment position. We don't have that. We know where the camera is, but we don't know where the current pixel being rendered or fragment being rendered is. So how do we do that? That's actually a bit more complex than one might imagine. There's no position that we can just read from that just works. We actually need to pass all of this data to the fragment shader from the vertex shader. And if you notice here, we don't actually have a world space position. We have the vertex here from the mesh data. That is in local space of the mesh, so that's not world space. In vertex output here, we have the clip space position, but that's still not world space. So what we need to do is to make another interpolator in the output of our vertex shader. So let's add that. Let's call it world position. Let's use the next interpolator here. So now we need to define the world position as an output here. So O dot world position equals. So what do we do here? So here we need to get the local space position and transform that to world space. So Unity has a bunch of matrices. You don't really need to learn how matrices work. You can just think of them as a way to transform things from one space to another. And the matrix multiplication thing in shaders is called mul. So basically multiply, and then you pass the two parameters. You need the matrix and you need the vector you want to transform, right? So we want the position to be transformed from local space to world space. So that is called something like Unity object to world or something. I'm gonna look it up because I never remember this. Where is it? I shouldn't have to use these. They did have a better helper that is like, oh, here it is. Object to world, perfect. All right, so now we have now we multiply this built-in Unity matrix. We have access to this one because we're including it through the Unity CG include here. Yeah, so now we can use this to transform the vertex from local space to world space, and then we have the world position of this vertex. Then we interpolate that because it's an interpolator, and that gets sent into the fragment shader. I'm going to explain why they're called interpolators very, very soon, because we're going to run into an issue soon where it matters a lot. All right, thank you so much for the follow. I cannot read Chinese, but I would say your name otherwise, but thank you for the follow. All right, so, right, okay, so we have the world position now in the vertex shader. We're passing it on through the output of the vertex shader. Now we need to read it in the fragment shader. And as usual, to debug, I usually just, throw in a return, float for, and then we throw in whatever value we want to debug. In this case, it's o.world position. And alpha can just be whatever, it doesn't matter. And then let's go back. Okay, does this work? So it's clearly not local space. It looks like, I don't think this is correct. I think it is something wrong, but, so let's see, we move this on the x-axis and it becomes more red. That makes sense, because then the position is more, towards the red side of things. Or no, this might actually work. I think this is correct. So this is now visualizing the coordinates, right? Let's make another object that makes it a bit easier to see. Let's add a plane. Who uses planes? God damn it. We're using quads here. Legacy things. There we go. All right, let's slap on our shader onto this too. Okay, so again, a very useful tool is to look at the Unity gizmo in the top right, or the point or movement translation gizmo when selecting objects. So it's red in this direction. This should increase over 1 meter. So if we create a cube, the cube is 1 by 1 meter. If we move this here, you can see that the this is now increasing from 0 to 1 across the meter cube. So the x-axis is definitely working, and we can assume that the other ones work too, because they all use the same transformation function, right? Yeah, so we can safely assume that this is now working. So all the colors should be within this cube right here, because that's values which is 0 to 1, right? Yeah. So we can kind of, this is like an RGB cube now. Okay, so it's working. Also, as an aside, I just love the aesthetics of just world space colors. I think it looks super nice. Anyway, sorry. All right, world position confirmed, working. Usually you have to like make sure that scale is like properly handling it, and like rotation doesn't make it incorrect and whatnot, but all of this is working fine. Good. Okay. So what do we do now? We've got world position. So that's fine, that's working. Go back to our shading. That's trippy. It was pretty trippy. Okay, so now we can access the position of the current fragment being rendered. Why is this useful? Well, so let's make another sketch. Because you have the your eye or camera here. I'm so used to VR. In VR, things are rendered per eye because you have 2 cameras, like 1 per eye, which makes things very interesting and weird. So that's why I sometimes say eye, but for the intents of this thing, let's do a camera. Here's our camera. There we go. So you have your camera, you're viewing some scene, right? And then you have some objects. Here's our objects. So what we need now, we have the position of this one. And remember, this is in world space. So, you know, if the world origin is like here somewhere, here's the origin of the world, here's Unity 000, right? The position of the camera, that's a vector from 0 to the camera, right? And the position of the fragment that we're rendering is a vector from origin to that fragment, right? So for each fragment, we have a different vector for the point that we're rendering, right? So what we want the direction to the camera, and that's simple vector math. So what we need to do is that we need to subtract. So if we take this camera vector right here, let's try to make it prettier. There we go. To this point right here. And then we want to get the vector from here to the camera, like that. So all the way from here to here. The way to do that is that we take the camera position and subtract this vector. So what that gives us is a canvas that is too small. There we go. That's not the same color. Okay, there we go. You take this vector, and then you subtract the position of the fragment. So basically, cam position subtracted by the fragment position. So you can just do a simple, you can just like append these vector on top of each other. So say we subtract this one, right? So that's this whole thing, but since it's subtracting, we negate it, right? It's going in the other direction, like this. So now we can add this on top of this vector. So doing that, we just take this chunk and then move it up to this one. We get something like this, right? So now it's the camera minus this vector, which is the same as adding the reverse version of this one. And that gives us a vector pointing this direction. So this vector is now this vector right here, because vectors don't have a position, but we do have this one going from this fragment to the camera. That's this vector right here. So that's kind of like basic math to get a vector from one place to another. You just you subtract the you take the destination, subtract it by this from the by the source, and then you get the vector between the source and the destination. So this is the vector we want, right? And then again, because we're, like I mentioned with normalized vectors, for this to be a valid direction vector, we need to normalize this one, because this one has a length that can be like anything. Like it can be whatever you want it to be, because the camera can be far away or can be close. In this case, we just want the direction. But say we wanted to do something like fog, then this distance matters a lot, because then this controls how dense the fog should be, right? So anyway, this is you can consider that to be the vector from the surface to the camera. That was a lengthy explanation, I'm sorry. But I hope it was relevant. Okay, so we now have the world position, right? So to get this vector, you do the camera position, subtracted by this one, and then we get this vector. So camera position minus world position. So that gives us float3. We can call it fragment to camera. Okay. So now I have the vector from the fragment to the camera. What do we do with this? Well, we need to normalize it now for this to be a valid view direction. Within shaders, it's usually called view direction. So let's stick to that, because if you're looking at tutorials and whatnot, they're probably going to use that term. So that is simply the vector from the fragment to the camera, but we normalize it, right? Because we need this to be a straight up direction vector. So we got the view direction. As usual, we can just debug this. Let's just see what that looks like, and we can verify if it's correct or not. So let's do another output of the view direction. And let's go back to Unity. Okay, let's think for a bit. What do we expect these to be? So these should point toward the camera, and this should be in world space. So we can again use the gizmo in Unity to determine, is this direction correct? So looking from above, it's fully green, which is pointing upwards. Looking from the x-axis makes them red, from the z-axis makes them blue, right? And then it seems to interpolate smoothly between all these. So it seems like it's working. So if we get close, we can probably also tell that there's going to be a slight difference in shading, because at the bottom, it's going to be pointing more upwards, because these vectors down here have to have a sharper, angle up towards the camera, whereas these over here are more like flat, pointing towards the camera, like almost being, completely planar. And that's blue, and that's the z-axis, so it looks like everything's working fine. So now we have the vector pointing towards the camera. What are we making? I am making a long lecture/tutorial guide on how to write shaders in Unity, and right now I'm doing lighting functions. Okay, so view direction seems to work. Good. What now? All right, so we have the view direction, and we have the normal direction, and that's all we need in order to do a and light direction, in order to do a specular highlight. So there are different ways of doing specular highlights. The most common ones are, or the traditional cheap ones that are not physically based rendering, is called Phong, and then we also have Blinn Phong. I think the most intuitive one is Phong, so we can probably start with Phong. Because Blinn Phong is a bit of a hack that just happens to look much closer to what reflections tend to look like. Yeah, so let's do Phong for now. So let's think about this. How do we want to, what color of the surface do we want, depending on all of these vectors now? So let's undo a few things. Okay, so say we have a light source over here. Here's our light source. Great. Might want to use colors for this. There we go. Think about the follow. All right, here we go. Say we have a light source over here. This is our light. And then we want to render a few fragments, like, you know, all the pixels across the surface, right? So let's see what, like, how we want all of this to work. So fundamentally, the specular highlights are based on reflections, like a very, very specific directed reflections, whereas diffuse lighting is kind of the average of all of the reflections, right? So what we want is to, are you using a table? What do you mean by a table? Okay, so let's see. What we need something that can change, or so how do we do reflections? That's the first question, right? Oh, a tablet. No, I'm not using a tablet. So it's something related to your view, right? Because your view is the thing that is angle dependent. So let's say we have a vector, or let's say we take the vector going towards a specific fragment, and then reflect that. So let's say we just bounce that one, right? So that means that this angle is the same as this angle, and it's reflected around the normal here, right? So that's the normal vector. So let's, God damn it. Here we go. That's a normal color. Right. Okay, so we have the normal vector here now, right? And again, to a reminder, normal vector is the vector pointing out from the surface, just directly out from the surface, right? So that's our normal vector. Okay, so now we can see that if we take the view vector, that's this vector right here. Again, it's normalized, so it should have the same length as just the length of 1. So this is our view vector. And then we can reflect that one. So let's make another one. So this is the reflected vector, right? So this one is a bouncing off of the view vector. You can imagine the view vector bouncing off the surface, and that's based on the normal. And then here we then have the view reflection vector. So let's call it VR. So that's the view reflection. So what we can then do is that we now have the direction to the light source, right? And as usual, we can do the dot products. So if the view reflection is pointing directly towards the light source, we want it to be very strong, right? If the view reflection is pointing away from the light source, we want it to be very weak. So how does the view reflection change over the surface? Well, the view reflection, if we sample this one right here, the view reflection is going to point further away from it, because again, it's bouncing off of the surface based on the view vector. So this one is going to point more and more away until the normal is perpendicular to the view vector, in which case the reflection vector just goes straight away, right? So you can see that this one is going to be turning towards the light source here. And then if you go up further, the reflection is going to be more and more pointing upwards like this. So this one is pointing almost directly towards the light source. Then it's going to be pointing more and more over like this. Then it's going to start bouncing off here, where it's going to start to like really take off over there. So all of these green vectors, that's the reflection of the view vector from the camera, right? Like this. Okay, so that's the so using these vectors in this way, as in directly reflecting the view vector, that's kind of the basics of doing a Phong specular highlight. Okay, so now we have all of these vectors. So what do we do with all of this now? Okay, let's go back to the shader. Okay, we have view direction. Where's our normal? We have the normal here. We're using that for the light fall off here. Okay. Let's use it again. So we need the view reflection vector, right? The one bouncing off of the thing. So how do we get the view reflection vector? Well, there's a handy function called reflect that you can use. And then you pass in the normal and you pass in the incoming vector. So we have the normal and we have the view direction. And then we can just return that just to make sure that it works, right? Again, because that's always super useful. Otherwise, it's going to be really difficult to debug this, like trying to figure out where in this shader is everything going wrong. It's super difficult. So I would recommend like always debug every step along the way in case you're not sure it's going to work. And in this case, I am actually not sure because I almost never use the reflect function. I don't remember if the normal is the first parameter or the second parameter. I don't know if the direction is incoming direction or pointing away from the surface. So I'm gonna have to try this. So this is view reflection vector. Let's see view reflect. Control space. Control space is not gonna work for shaders, I'm pretty sure. Yeah, there's no syntax highlighting for shaders. Or no, wait, there's syntax highlighting, but there's no autocomplete, so which also sucks. So welcome to shader coding. Let's look at we can actually look this up. So there's a NVIDIA CG. There's a documentation for CG here. So if we go to reflect. Incidence vector, normal vector. Okay, incidence vector sounds like it's pointing toward the surface rather than away from the surface. So we were completely wrong. So let's move it about. Probably negate the view direction because it's the incoming vector, not the vector pointing away from it. Okay, so let's see if this works then. All right, let's just output the view reflect vector and see what that looks like. Okay, now we have to do the same thing again, like use the coordinates in the top right to like figure out is this correct or not. It sure looks pretty shiny, right? So if you remember looking back at the Photoshop thing, as soon as we got to the edges here for the view reflection vector, they started like pointing just straight up away from the camera, right? Because these just bounce off, right? Whereas here they're pointed directly toward the camera. So we should expect looking from above it to be green because that's moving directly upwards. And again, looking at the other axes, we have red on the x-axis, blue on the z-axis. Now for this part right here, if these point toward a specific axis, we should see a glow of color here and here, or like around the whole mesh. So let's make it reflect toward red on the x-axis, and yeah, we can see that it's red around the edges because all of the vectors bouncing off of the edges kind of just continue forward, right? And that direction is the direction of the x-axis, right? Fresnel shader 101. We haven't actually made Fresnel yet, but this is close to it, right? Yeah, this is like a world space aligned Fresnel, but anyway. Okay, so now we appear to have a vector that is actually pointing in the correct direction. So let's go back to this thing. So that vector that we just visualized was a view reflection vector. So what's left to do now is to do the dot product between the view reflection vector and the light direction. Is this used for game dev? Yes, it's used for game dev. It used to be used more back in the days, because now if you're doing AAA games or like like games with high rendering quality, then you tend to use PBR, which is physically based rendering. But and PBR is similar to this in that, you know, you have a fragment, you have a bunch of vectors, and then you combine them in a very specific way. But the thing is, like, PBR is way more complicated than this. But the whole function of this whole function of having a bunch of vectors and parameters to determine the final lighting of this thing is called a BRDF, or yeah, BRDF. I think it's like bidirectional reflectance distribution function. What? Okay, can confirm. Good. Yeah, so BRDF is the term used for this operation where you have a bunch of vectors and you want to get a lighting output from that, right? So it's a BRDF. BRDF. So if you want to use a PBR, the BRDF is going to be way more complex. But in my case, I just have Lambert diffuse lighting and Phong specular highlights. We're not done with the Phong, so let's do that. But yeah, I think the more like standard or simple lighting stuff, that's probably still used. Probably not much in like I mean, probably not in like the very high quality games. But if you go from mobile games, high quality, I mean like very advanced rendering type of games. But if you go for like a mobile game or like any game where performance is a very like sensitive thing, you might want to use like these more simplified functions because they're way cheaper, right? Why do we create a vector from the object towards the light and towards the camera, not from the camera to the object? Oh, why the vectors are pointing in this direction? It's probably just because the math turns out to be cheaper that way, because we can just do dot products and it works out. Whereas if they were reversed, it would be more complicated. We would have to like reverse them in the math. Anyway, now we have the view reflection vector. We know that this works. Now we need to do the dot product between the view reflection vector and the lighting vector, right? Or the light vector, like direction, I should say. So let's go back to the shader code. Have view reflect direction. Okay. Float, specular. Let's call it specular. Fall off was the term I used for the other one. All right, again, dot product. We want to do the dot product between the view reflect vector and the light vector, right? Okay, so this is our specular fall off. Again, let's debug this. Let's just like throw this value out, see what this looks like. There we go. Okay, so this is starting to look like a very, it's a very matte, shiny reflection, right? But it does depend on the view direction, right? You can see that it kind of wraps around and changes. So that seems to work. Now let's do a few more things. Again, we had the problem of negative values in the dot products. So we want to remove those by doing the max 0 and then the dot products. It's going to look the same because negative values are just 1. But yeah. All right, so now we have that. So let's see, we might want to be able to control this. We might want to be able to control the glossiness of this object, right? Because now negative values are just 1. Oh, they're just 0. Like, well, the output on the display, if you give it negative values, is just 0. Sorry. So, okay, so now let's modify the glossiness of this. This is a very common thing to do, you know, should it be very shiny or not shiny at all? So let's make another parameter for that, so we can like control that per object. All right, there we go. And this is just a float, right? Or we might want to make this a range between like 1 and a lot. I don't know. We're gonna have to modify this one later. Actually, let's just make it a value or floats. I cannot keyboard. Okay, so now we have a parameter so that we can change the gloss. So I saw shader stuff and so I clicked welcome to the stream of shaders. Okay, so we got the gloss and now that's a parameter that we can control. Again, let's just output the gloss. Let's see what that looks like. Right, we need the variable for the gloss. Right now we didn't define that. So like the color, we also need the variable inside of the shader itself. And this is a float. And let's see if that works. There we go. Where's the song tracker? It's broken because I have a different computer and I didn't have time to set it up. But you can do exclamation point song in case you want the current song. All right, so this is now outputting 1. So if we look at this, shader right here, or this material, we can now modify the gloss value. So if I lower this one, it gets darker on this material, which is what we would expect, right? Because we just returned the gloss now, and 0.5 is darker than 1, and so forth, right? So that's working. We now have a way to control gloss. So how do we control gloss? How do we actually make that? The easiest way to set that up is to do a power. You take the power of, let's see, you take the specular fall off and raise it to the power of the current gloss value. And then you have modified that one. So modify gloss. There we go. So now we're basically taking the value, raising it to the power of the gloss, which is, if you do some value to the power of 2, the 2 would be the gloss value. Like mathematically, that's what we're doing. All right. So now we have the specular fall off, and let's see what that looks like. Recompile. And then let's go to this shader right here, and then see what happens when we change the gloss value. So if we go very low, we get to incorrect math. If we go very high, you can see we get to a very shiny little highlight, right? And that's what we want, right? All right, so now you see we got this little specular highlights wandering around the way that we want it to. And that's pretty good. So let's change the gloss value of all of these to be somewhat high. Let's have one of them be matte, because why not? So why is everything reversed? There we go. That's better. All right. Doesn't exactly help that these are called simple shader instead of material. Can I recommend any reading material for shaders? Yep. For Unity, for learning how vertex shaders and fragment shaders work, I recommend this one. That's where I learned like 5 years ago. It might be outdated at this point, but it's very good for covering the basics. That's where I started. Or my stream. Feel free to come here and ask questions. I stream game dev here generally. And I'm always open to questions if it's, whether it's about how to do things in Unity or in game dev, or even within the industry, or like how to navigate things. But yeah, I tend to be very, very open on my stream. This is kind of an exception. I tend to not do like 100% lecture type streams, but I tend to kind of talk about what I'm doing and why whenever I'm working on games. Right, I wanted to make the gloss different for one of these. There we go. Let's have one of them be a bit more diffuse. Okay, so some of you may have noticed a problem with this, or depending on the art style you want to achieve, you may have noticed that this is extremely faceted, right? You can kind of see the triangles wandering around in this one. Same thing if you go to this one, it's kind of like a grid. And I'm guessing that that's not what you want to do, right? So now we're going to talk about interpolators. Interpolators are important. You need to know how they work. The problem, let's do this problem in 2D because that's easier to get a grasp of. Actually, let's keep this color palette. That's useful. Incorrect. There we go. All right. Now let's talk about interpolators. Okay, say you have a mesh. We're looking at the mesh from the side now. We have vertices, right? We have edges going between the vertices, and so forth. Maybe this is a very low poly sphere or something. So this one is it's got 5 edges around the whole thing. but this is a low poly sphere. We want this to look like a sphere and be, yeah, just look like a sphere, right? So this is a smooth shaded thing. So if we go to Maya, for instance, we create a sphere, it would be equivalent to, wait, where's, oh, there we go. I mean, something like this, right? Like a very, very low poly object, but you want it to be smooth. So we soften all of these edges. There we go. So now you can see that this one is like more smoothly shaded, even though it's super, super low poly, right? So this is kind of the situation we've got now in this example. So this is a more extreme version of the problem we had with the spheres in Unity here, because these are a bit more high poly, a bit more, quite a lot more. Okay. Back to Photoshop. So, now the way things are structured in shaders, remember that we have the vertex shader, or basically we have the mesh, right? We have the mesh data. We have the mesh data, that one sends data to the vertex shader. The vertex shader passes that on to the fragment shader. There we go. So we have this kind of pipeline of things being passed to another thing, right? So if we go back to Maya, if we look at, where are the normals? They are just per vertex, right? The normal between vertices is just not defined. It's not data that exists in the mesh. We just have it per vertex. So what we got is that each vertex has the normal data, right? So we have a normal here. We have another normal here, because this is smooth shaded, right? So we have a single normal, that's kind of the average of the normals of the faces next to them, right? If this was a hard edge, we would have two normals, one pointing in this direction and one pointing in this direction, this belonging to this surface and this belonging to this surface right here. But this is soft edge thing, or yeah, soft shaded thing. So this one is gonna have normals just pointing like out in this direction, right? Okay, that all makes sense, right? So far, so good. Now, remember that the mesh data to the vertex shader, that's just passing data along in a very normal way, right? But when we go from the vertex shader to the fragment shader, there's something that happens. And that is because we have this triangle and we have vertices on each corner, right? Now, the problem that appears, or that is in front of us, is that we have a normal for this one. Like, we do have a normal vector here. We have a normal vector here, we have a normal vector here. But the question is, what is the normal vector in this location? So, so this is why the whatever you've passed from the vertex to the fragment shader, those data fields are often called interpolators because we don't have data here. We don't know, like, what's the actual normal inside of this triangle, because these can point in various directions, right? So what happens is that there's a blending function that takes all of these, all three normals into account when trying to figure out, what's the normal of this point right here? What's the normal of this point? What's the normal of this point? And so forth, right? So what it does is that the closer you get to this one, the more it's going to resemble this normal. The closer you get to this normal, the more it's going to resemble that, right? So if we visualize that in 2D, we have this vector right here, and then all of the other normals are going to lie along this line right here, because it's a linear interpolation. So the center normal here is just going to point like this. This one is going to be slightly angled like this. This one is going to be angled like this, and so forth. So these are the interpolated normals. And this goes for everything you send from the vertex shader to the fragment shader is interpolated like this. So for instance, hold on, I'm undoing. Actually, let's keep this. There we go. So that applies to anything you have. So that could be, say you have vertex colors. You have one color here, one color over here, and one color over here. So then if you ask the question, what's the color like here, for instance, it's going to be a blend between these two colors. So we're going to get, so I don't, hold on, this color. So now you can see that this is a color that's like a blend between these two. So instead of just being like a harsh cutoff, like a harsh cutoff or something would be like, you know, this green color is only in like this area right here, like here, and then you have this one in this area and so forth. That would look pretty bad. So what happens is that they are interpolated. So we get like smooth data like this. That way they are kind of like, yeah, properly, we can properly get that color per pixel, right? So that has a side effect. So if we go back to this one right here, remember that normals have to be of length 1 for them to be valid in all of our lighting calculation, right? So if this one is length 1 and this one is length 1, but we interpolate between it, then what's going to happen is that these are going to be too short. This one is going to be slightly shorter, because if you imagine something like a square here, and you have the normals pointing in the diagonal like this, too short like Destiny. Wow, all right. Shots fired indeed. There we go. Okay, it's a bit more clear in this example, right? So now the length of 1 would be like in this circle right here. But if you look in the center, it's too short. It doesn't go up to the top of this little circle, right? So the that's selection. Here we go. So the interpolated normals that we're going to get in the fragment shader, it's all of these vectors. But what the vectors we want should lie along a line more like this, right? Because I want these all to have the length of 1, right? Then it's going to continue circle around like that. Yeah. So what we need to do is we need to solve this problem. So how do we do that? Well, we actually do have a function called normalize. So what's happening here is that these are too short, and we need to normalize it. So let's go to the shaders again, and let's go to our normal. So that's in the input of this one. So let's define the normals here. Normal equals o dot normal, and then replace all of the o dot normal we had here, because we're making this into a variable now, inside of the fragment shader. So we go back, it should look as bad as it was before. Perfect. Okay. So now that we get the normal from the vertex shader, we need to remember that this one is interpolated. And that means that the length of this one could go below 1. So we normalize this one. And then we get, then we go back, and there we go. So now the normals are properly interpolated, where we normalize them again after the interpolation, which made them incorrect. And now they're fixed. So now we have this smooth highlight instead of the shitty faceted thing. Unless you want that faceted look of your game, in which case then go for it. Yeah. All right. Did that make sense so far? Also, if you, in case you want to look into the interpolation and whatnot, this type of interpolation is called barycentric interpolation. If you want like a very simple explanation of how it works, is that if you imagine a point, like say you have this one, for instance, you want to get this point right here, then you can imagine forming triangles in all of these regions, right? So if we just draw lines to the point, then the area of this one is going to be is going to act as a weight for how much this should influence the color. and the area of this one is going to act as a way to determine how much this is going to influence the color, and so forth. So then there's a lot of yellow in this one, right? The area of this one as a percentage of the whole triangle is going to be very big. Therefore, it's going to be very close to the yellow one. That's kind of the basics of barycentric interpolation. Oh, show the code again? Sure. Let's see. Think about the follow. Return flipped for negatives. What I have negative specular fall off? Playlist link? Sure. I added a command called playlist, so you can just like do that. And then this one is the lo-fi playlist. It's available on my profile. Is there a way for fast normalizing without using square roots? Probably. I've never used that one personally, but yeah, it is expensive to do it. But I mean, it depends on the platform. If you can avoid it and you can retain your art style and whatnot, then go for it. But yeah, it's just up to the current like project and your like performance goals and whatnot. I need to drink water. I just realized. Heck, I totally forgot. How are you thinking about the direction we're going so far? Is it useful? Are you feeling like you're learning stuff? And there's just something that you feel like I didn't cover that I should cover? I'm thinking by the end of the stream, I can go into showing a few examples of the shaders that I've done in ShaderForge. Is normalize the only interpolator, or are there more? Find out what interpolators are correctly. Oh, so the output of the vertex shader, all of these are interpolated. So these are interpolators. We have 3 interpolators in this. Well, 4, I guess. So 4 interpolators. I actually don't know if this counts as an interpolator. It should, I guess, but yeah, so we currently have 3 of them right here. We don't need to normalize all of them because we only need to normalize the things that need to be of length 1. Yeah. Yeah, it's cheaper not to do it, so. Will the video be available tomorrow? I'm not sure. The stream crashed earlier, so I might have lost the very first bit of the stream, which I really hope not. But it's going to be available on Twitch. The only problem is that Twitch is probably going to mute part of the stream because of the music. But I'm going to upload it to YouTube as soon as I've been able to recover the first one and combine all of the other things, right? Does Unity automatically normalize your flow 3 if the keyword is normal? I highly doubt it. So we can try, I suppose. So let's go back to this one. That's incorrect. Also incorrect. Too many things running. There we go. Okay, it's faceted and bad. Back to this one. Normal. No, it doesn't do that. Yeah. I'm gonna try to recover the video as much as possible to see if we can yeah, get it working again. Okay. Right, we still haven't combined all of this. We still have the problem of like we only have the specular light on its own, and then we have the diffuse light on its own, but we haven't combined them, right? So let's do that. Okay. To say recordings from OBS directly than before doing FLV can be dropped into multiple footage. I can't do FLV because FLV doesn't support multiple audio channels. I do MOV, I think, MOV, because MP4 had some issues where it didn't support, or didn't like work with the audio channels for some reason. Like it says that MOV is not recoverable because it's like broken, but I'm thinking there might be some tool where it's like, oh, I lose some header data, but I might be able to like reconstruct it if I just supply some data manually. If there's a tool for that, I'm guessing. So that's what I'm going to look into. It might work. I don't know. I don't know how that file format works, but there should be some form of data that I can convert to correct stuff, I'm guessing. Unless that header had compression data, in which case it's over. Okay. All right. Let's combine all the things. Let's see. Direct specular light. We still haven't done the whole thing. So we have the specular fall off. Then we modify the gloss. Okay, so this one still isn't colored by the light, so we need to do that. So specular fall off. Let's multiply that by the. Actually, let's do direct specular. That should be a variable. Direct specular equals specular fall off multiplied by light color. Or wait, we had light color up there. Good luck. Thanks, Atras. Let's see. These are kind of not directly related to diffuse anymore. Okay, so I had direct specular about ambient light. Okay, so we just need to composite this now. So let's comment this out. And then in the compositing step, we have diffuse light, that's multiplied by the RGB color, and then we add the direct specular light. There we go. That should be it. Oh, we forgot to normalize the thing. That's not where you normalize it. That would actually not help at all. There we go. So now we got some heckin' spheres. We can tweak the gloss value if we want it to be super shiny. And yeah, that's the basics of that. There are a lot of like nuances in terms of like how you want to combine these things. Like, should the surface color affect the specular color? Should the specular color be different from the incoming light color and whatnot? So there are different ways of setting this up. It kind of depends on how you want your shader to look. In PBR, it like depends a lot on whether or not it's metallic, or if it's like dielectric. Yeah, so there are a lot of factors that go into like more advanced lighting functions, but yeah, that's kind of the basics, I think. And not the same thing again. Okay. All right. Is there anything you want me to go through? We kind of almost only talked about lighting at this point. We haven't really done any like math shenanigans. Might be fun to talk about transparency. Sure. Transparency is generally not fun because there's a lot of issues with sorting in transparency. But yeah, we can definitely talk about that. It's actually like the general concept is blending. We haven't even talked about that. So yeah, we could do that. Or texturing, sure. Oh yeah, textures. Is cell shading a quick thing? I'd love to see if it's fundamentals. So yeah, that would probably be pretty straightforward. Basically what you need to do is you threshold the lighting. So that's actually very close to what we've already got, right? So let's say we take the let's do, where's the diffuse light fall off? That's this one. Okay, so we have the light fall off here. So we can threshold this one by doing light fall off equals step, then 0.5 or whatever, or maybe a bit higher, and the light fall off itself. I might have reversed this one, we'll see. There we go. So now we have like this very, very sharp edge for the for the lighting, right? So in this case, we probably want to use like a different value. That's a bad value to use. So now we have this like very sharp cutoff there. Then we might want to do that for the specular highlight as well. So again, we just do the same thing for the specular fall off. I can explain how it works in a bit. So, whoops, forgot to replace the thing. There we go. So now I have this like very cartoony highlight thing. Yeah. So that's how you would like start doing something cartoony. There's a lot of like, there's a lot of nuances in how you set this up, but this is kind of the basics. You have your normal lighting functions, and then you kind of remap them to be a bit more cartoony, right? You make the gradation between the shade sharp instead of smooth. Yeah. Can you explain how step and smooth step work? Yeah. Okay. Let's do this. So I might explain this in a bit too mathy of a way, but I think it's useful. So let's say you have this value between we have 0 and 1 here, 0 and 1 here. I say it's linear, so we got this graph right here. If we want to change this one so that so right now, let's say we have values between 0 to 1, and then they just go in a linear blend. That's just going to be a gradient. Actually, I can show that in a much better way. Hold on. There we go. Hello, quad. Let's add the same shader to that one. That's a light source. Okay, let's hijack something as our gradients. So I'm just gonna do return uv.x. No, y. Okay. Say you have this gradient, right? This is similar to what we have with the lighting. We have a value going from 0 to 1 or something. Or in our case, I guess it went from like -1 to 1, but okay, so if we want to make this a harsh cutoff instead of a soft one, we can use a thing called step. So what step is that it's kind of like a comparison. It's kind of like if value is less than, let's see, like if A is less than or equal to B, return 1. Else return 0. It's something like this. I might have reversed the less than greater than, but this is kind of what the step function does, where you have step A and B. So say we want to threshold this value now, then we can do step UVY, and then we have some threshold. So let's say we want to do 0.5, that should be in the center, right? So we recompile, and now you can see that we have a harsh cutoff in the center, extremely just sharp. Yeah, and then if we move this one to 0.25, it's going to shift. So this is kind of just a very simple way to say values above this should be 1, values below this should be 0. That's it. It's a very simple like way to blend those things, or to change the fall off of something. Smooth step is kind of unrelated, actually. Heck, I feel like I should explain lerp and inverse lerp before explaining smooth step. Let's do lerp. We haven't talked about lerp somehow. How we had a stream, multi-hour stream, and I have not done a single lerp. So let's actually fix that. Let's say we want to do color. Or actually, let's just output uv dot y. There we go. Okay, let's go back here. What function moves in x size increments rather than cutting off at the number? What do you mean by moving in x size increments? if you would just want to change the rate of the gradient, you can multiply it and then subtract or add to offset it. If that's what you mean. Anyway, okay, so lerp, super useful. If you've used it, you probably know how it works in C# or with values, but you can do that with colors and whatnot too. So say we have this gradient and we want to have two different colors. Like we have a color at the top and we have a color at the bottom. How do we do that? So lerp is very similar to the interpolation where we're talking about here. You can think of the interpolation between these two as a lerp between this one and this one, where the distance along the way to the next one, that's not how you do this, there we go, where the distance here would be a percentage called a t-value. So this would be like 0.5 or something. So if this is A, this is B, and we do a lerp between A and B, and then T would be the percentage here. Then what we get is a blend between these two, which you can use for colors, you can use it for positions, you can use it for all sorts of stuff. This is probably a dumb question, but I remember I had difficulty with this. Are there ifs and elses in HLSL? It's not a dumb question. Don't worry about it. There are ifs and elses in shader coding, but you do want to try to avoid them because if statements and conditionals are very expensive, or well, not very expensive, but it can be very expensive depending on how you use them. So in general, if you have like two simple math functions and you need to alternate between them based on something, quite often it's cheaper to calculate both of them and then multiply one of them by 0 and then add them together, rather than make an if statement and then return something else if you based on the state, right? So quite often you just run the math of all the branches and then just like kill the branch that you don't want to use, right? I heard lerp is not super good for performance, or a common case where something cheaper can do the same. It depends on what you're doing, but you can do other things. You can use something other than lerp. Yeah, but I mean, lerp is, if it's expensive for performance, that's probably on a like very performance sensitive platform. Because a lerp is generally not expensive for if you're doing like desktop stuff. But yeah. To me, step takes a linear 0 to 1 and makes it, oh, you want like incremental steps from like, okay, so 0.1 step size, okay. That's a bit of a different thing. You can't do that using the step node, or it's a node. I'm not using a node-based editor. You can't do that using the step function. There are ways of doing that though. I can show that if you want, but I just want to go through lerp first. Okay. We want one color at the top, a different color at the bottom. How do we do this? Well, first we need the two colors, right? So again, float3, RGB, color, color A equals, and then we get a value. I don't know what color we want. Perfect. And then we have color B. Great. There we go. Okay, we have two colors. So let's blend between these two colors, and we do that using lerp. So float3, blended colors. Let's just call it blend. So that's going to be a lerp, which is short for linear interpolation. And then we interpolate between color A, color B, and then the t value is going to be what controls where we want A and where we want B, right? And in this case, we want to use the y coordinate of UV because we want, down here we want one color, up here we want another one, right? So this is going to be our t value for the function. That's the third parameter of the lerp function. So we give that one uv.y, and then we output the blend. So now, yeah. Now we should see something that's like the blue at the bottom and then something red and purple-ish at the top. And we need to fix that first. And we need to float 4, not magenta all over. There we go. Yeah, so now we have a gradient between two colors. So this is something that lerp is super useful for. So now all we did was define the two colors at the top and the bottom, and then you take these two colors, interpolate between them based on the UV coordinates here, and then you get those. What does the lerp function do? It's an interpolation. It blends between these two based on the third value. That's what it does. Yeah. All right. Aesthetic. It is pretty aesthetic. Why float 3 blend 0 and not blend? Because we're returning a float 4 in this whole function, and blend is a float 3. So we need to define the alpha channel as well. So I don't think we can do this. It's going to be sad now. Yeah. But yeah. What's the difference between normalization and lerping? They're very different. So what we did here was that we were lerping normalized vectors, but normalization is a different concept in and of itself. So normalizing means that you take a vector, you make sure that its length becomes 1. If it's too short, it becomes 1. If it's like longer, if it's too long, it becomes 1, right? So it just shortens, and if it's too short, it extends. Yeah, anyway. So normalization is you take a vector, normalizing makes it have the length of 1, but it has the same direction. Unless it's 0, like 0, 0, 0, in which case the normalization is an invalid operation. But yeah. Linear interpolation is just that you have one thing and then you blend into another thing, whatever it is. It could be vectors, it could be colors, it could be positions, it could be anything. Yeah. It could also be simple values. Okay. So now we can do this for like, so let's say we do have the t value here, and that's going to be our uv.y. So let's just call it t, it's still working. So now we can, let's say we do a step on this one. 0.5, and now the value is going to be either 1 or 0, right? So now we get this really harsh fall off again, but with the lerp function. So now we actually get these two colors on these two positions, right? That's all well and good, right? But let's say we want a blend between from a specific place in this gradient. So let's just view the t value now. So now this one is a harsh fall off. What if we want this to be a bit softer, but the step function is too harsh? And this is too soft. So let's say we want the gradient to be between somewhere here and somewhere here. Then we need to change the range of this one. So in order to do that, we kind of need to do the opposite of lerp. So what do I mean by opposite of lerp? So okay, let's do some. This is going to get a bit math heavy, so apologies for that. So if we want to write a lerp function, let's say lerp didn't exist in shaders and we had to write our own. Make the shapes rotate. That's going to get complicated. Let's say we want to make a lerp function between float3 values, which would work for colors, right? My lerp. There we go. Then we have float3a, we have float3b, and we have float t value. The t value is always just a float, right? It's always just a percentage. Okay, so if I want to make a lerp, the mathematics for that is pretty straightforward. So then we want to return t multiplied by b, and then we add 1 minus t multiplied by a. I'm pretty sure this is the lerp. To make sure, let's try it out. Let's see. Okay, we're back to the colors. Replace that with our own lerp. Looks exactly the same. Perfect. Okay, so this is a lerp function, right? So what do we actually get out of this one? We get a value, right? We get a value equals lerp, and then a, b, and t, right? So what is an inverse lerp? That's kind of the other way around. So we want to make an inverse lerp. what happens is that we, instead of returning a value, it returns a t value, and then we give it a value. So basically, in more like practical terms, it's like you say, I want this value to this value to be 0 to 1. That's kind of the question that inverse lerp is answering, right? So we can make an inverse lerp function. This is something that is not really built into shaders, except for smooth step, because smooth step is actually a bit of a weird version of inverse lerp. So let's make an inverse lerp. So that's a float return value, and then again we have a and b. And then the third parameter is a value, and that's going to be float3 in this case. Wait, inverse lerp gets complicated with vectors, so let's just do a value for inverse lerp. Value, there we go. Okay, inverse lerp, if you just do the math, reverse the whole function, the inverse lerp would be value subtracted by a, and then we divide that by b minus a, and that's the inverse lerp. Okay. Give me the percentage between a and b where v lies. Exactly, like Risperity is mentioning in chat. All right, so now I have inverse lerp. So what do we want to do with this? So as I mentioned, I wanted to change where this gradient was starting and ending, right? I wanted it to go from here to here. So I wanted to kind of squeeze it together, right? And these two values, what are they? They're like 0.75 and 0.25, right? So let's do an inverse lerp of this t value before we use it for the gradient. So let's do inverse lerp, and then from 0.25 to 0.75, and then we have that one over there. So and then the linear gradients going through that one, and then you have t here. Can you make the blending area smaller? That's what I'm doing right now. So now we have remapped this one. So instead of being, you know, 1 at the top, 0 at the bottom, this one is now going to get squeezed together like this. So now 0 lies here instead, and 1 lies over here. So that's kind of what we did now with the inverse lerp, because we just told it to, you know, wherever the value is 0.25, I want it to be 0. Wherever the value is 0.75, I want that to be 1 within, given the value that I provide, right? And that's what it did. One thing that you should note is that lerp, and I guess inverse lerp in general, are not clamped. So we actually have values above 1 here and values below 0 here. So we might want to be careful like how we use that and whatnot. This sounds like something you could theoretically use for black bars on the screen during cinematics, and like, yeah, sure, you can use this for whatever you want. Like there are lots of different ways you can use this. Okay. All right, so smooth step. Now we're finally back to smooth step. Smooth step is a very, very strange function. Smooth step is an inverse lerp, but it has a smooth curve applied to it. It's very bizarre. I don't know why it exists, but it exists. So we smooth step this one. It works pretty much the same way. It's just that there's a curve applied to it. So it's like an ease in, ease out function to the gradient here, instead of being linear, right? But why shader languages have a smooth step but not an inverse lerp is, I have no idea. It's very strange. Why is there no inverse lerp? Makes me sad. But anyway, so smooth step is an inverse lerp with a smoothing function applied to it. Yeah. Thank you for the follow. Okay, that's some heckin' math. Now we can use this for the blending thing again if we want to get the colors back, and now this is in a very like short range. So if we move this one closer to like 0.45 to 0.55, it's going to be a super tight range in the center here, right? Okay. All right. Did that make sense? Any questions? Any thoughts?
Looks like incorrect.
Yeah, it is. Don't stop. Shush. We're not getting into gamma. Oh, who was it? FemFluid asked a question. How to make this like, have a step size of like increments instead of like, wait. So the difference is it's not linear, but east and out kind of spline. Exactly. Yeah. God damn it, Steve. Stop it. We're not talking about gamma. I agree with Kperia in chat. What was I talking about? I lost track because of gamma. Right. The question about oh, this is cute. Right, making like a step thing that's like has a few steps instead of the literal step function, which is just a threshold, right? All right, so how do we do that? Let's go back to our gradient that we had before. There we go, and then let's just return the t value again for visualization purposes. All right. What do we do with this? We want to make this like be steppy, right? A very nice way of doing this is kind of think of it as like a rounding function that you can use, because what we want to do is we want to get stair steps instead of a soft gradient, right? So what you can do is we take this value. Let's see, well, we can just do t, I guess. T equals t times 8, and then we round this value, and then we divide it by 8 again. This is a very like simple way to get like round something, but to a certain precision, right? So if we go back to Unity now, we now have this like steppy thing that's like posterized is a term that's sometimes used for this. Or you can use like floor, you can use whatever you want, depending on how you want it to be aligned, right? Yeah. Yeah, so you can do that. Why is graphic programming so much floating point? Wouldn't it be faster if you calculate integer values? Yeah, like Steve is saying, it's very much like optimized for floating point stuff. In this way, returning to the cell shading shader, you would assign number of shades. Yeah, pretty much. So I mean, we can make a function out of this too. Let's make that. Let's make a posterize function. Posterize. Then we have the float number of steps, and then we have the value, right? And then we just do this thing. So return. There we go. Return. Instead of 8, we do steps, and then we have value instead of t. And then we can call the posterize function, where the number of steps is, let's do 16, and then the value is t. There we go. So now we have a function called posterize. So if we wanted to, we can use this in, we can use this for the lighting if we want to, right? So all we need to do is to go to the fall off functions again, and instead of step, we now do posterize. The specular fall off, and go back, and now we have this like all of these rings, right? Yeah, probably don't want to use that many segments, but the same thing goes for the light fall off here for the diffuse lighting too. Yeah, this is a weird little way of doing the cell shading type of thing. Yeah. Celestial Vamp, thank you for the follow. Whew, I have not had enough water. Starting to get a headache. Looks like the specular is inside. Yeah, sort of. would be amazing rendered at a low resolution. Oh, never mind. I was gonna do some shenanigans, but never mind. Yeah. All right. What else? Is there anything you want me to go through? Is there anything you're curious about that I should try? Otherwise, when I'm gonna round off the stream, I'm gonna try to I'm gonna show a few things that I made in my game in case you're curious about like how shaders can look when you spend more time on them. A bit off topic, what's the difference between fragmented surface shader? Try combining two shaders in one by apparently they're incompatible. So surface shader is a very, very like specific thing that Unity has set up to make to make certain things easier to do because they kind of automate a bunch of that process, right? Thank you for the follow, pizza service. Hello, Harry. I recognize you from Twitter. Thank you for the follow, Flores. Multiple light support. We haven't talked about multi-pass shaders. Let me double check to see if Unity has a single pass structure set up for lights. Might actually have that. Not important point lights. You can do that, but basically that depends on your rendering pipeline quite a lot. So like if you're familiar with the term deferred rendering and forward rendering, these work in fundamentally different ways when it comes to lighting. The stuff that we've been doing now is very like forward rendering, that type of shading. Yeah, I don't know. I don't think we should go into the rendering pipeline stuff right now. Let's see. Someone asked about things affecting other things, like if you want the, let's see. Oh, how do you do shaders that react to other objects in the scene? Right. So fundamentally, it's kind of the same thing that we've been doing already. It's just that you need to pass data into the shader. So you can use properties for that. If you need like the position of the player or something for your stuff, then you can pass that in as a thing into the shader or as a global variable. Do you want me to show you how to do that, or what do you think? Because I could do that, but it involves a bit of C# as well. What if we wanted to show the red sphere's reflection onto the blue one? Oh boy, that gets very complicated very quickly. There are a lot of different ways to solve that. All of them are expensive pretty much unless you pre-bake it. Stuff like that is super not straightforward, but it's way easier to set up in like if you do like a ray traced thing, if your whole shader pipeline is ray tracing, or path tracing, I guess, I don't know. Like that gets easier because then you can just like do the vectors. The problem is that in each shader for each object, you don't have access to the neighboring objects, right? You only have the data for that object and whatever parameters you pass into it. I mean, in Unity, you do have, you can bake like reflections and whatnot into a cube map and then have that on the texture. But yeah. Can I make the spheres glow when the mouse gets closer to them? Yeah, sure. I can do that. It probably doesn't take that long. Let's where's the camera? All right, let's set up the camera first. kind of want the grid, but anyway. Okay, do we need a surface maybe? Let's do that. Let's make a quad. +0. What a coordinate. Okay, we got a surface. Let's center these objects. Maybe not make them hover. Or actually, it's probably more easy to see that it's working if I keep intersecting them like this. Let's apply the surface thing to the ground like that. Maybe grab paths would be a cool thing to show. We could do that. I haven't talked about blending though. I think I need to do that first. Otherwise, because I think that's an important thing. Like transparent shaders is not something I've been, yeah, that's not something that I've been talking about yet. What about simple ray charging? You mean ray marching or? Yeah, I mean, we could do that, but that's not as relevant for games. That's kind of like, I don't know, I want to try to keep this pretty relevant for learning how to code shaders specifically for games, right now at least. Ray tracing is super fascinating, and I could do that, but I think that's out of the scope of this stream. And I think my knowledge with that is mostly related to like sign distance field ray marching, or not ray marching. I guess that would be whatever, you know what I mean, sign distance field stuff. I'm only on that, not like actual, like, you know, setting up reflections to intersect that with triangles and whatnot, but yeah. Anyway. What was I gonna do? Oh, somebody asked about like how I can make the things glow when my cursor gets close. I think that's a good example of like how to pass data into shaders and how to connect this to your games. I think I'm gonna talk about that. I want to change the light color. I don't like the yellow that we got on the ground there. There we go. Okay. This requires a C# script, but sure, why not? Okay, so it's a mouse glow thing. There we go. Thank you for the follow, SQPL. All right. So let's see, how do we do this? This should be in an update loop because we want this to happen every frame, right? So every frame we want to trace a ray from the cursor to the ground. And this one happens to be at 0, so we can just intersect the mathematical plane if we want to, instead of like doing colliders and whatnot. All right, so we got the normal on a point. Normal would just be vector3 dot up, point would be vector3 dot 0. Right, then we need the ray from the mouse. So we can do get component, camera, and then screen point to ray, and then we need to send this the mouse position. So let's define that. Input dot mouse position. Throw that into this one. That should give us a ray. Good. And then we do plane dot raycast. Okay, and that's an if statement because it could theoretically miss the plane in case we're like shooting the ray in the opposite direction. So that one returns true if it does hit. So we provide that to ray. And then we get the distance at which it entered the plane along the ray. Enter distance or something. Okay, so we got the distance now. Now we need the point at which it hit, right? So that would be ray.get point at that enter distance. So there we go. So that's a vector3. Mouse position, or like world mouse position. Yeah, there we go. All right. Get component inside an update function. Hey, I'm not showing optimized C# code right now. I'm just doing things to show how to pass data to shaders. Okay, all right. Let's pass this to shaders now. So now we do have the mouse position. I suspect that this might not work correctly because the mouse position might be flipped on the y-axis, but we'll see, I suppose. Okay, so now we can do shader dot set global vector, and then we need to give this an ID. There are optimized ways of doing this instead of using a string, but we're just not going to care about that. So now we're going to call this mouse position, and then we're going to set that to the world mouse position. All right, so that should be enough to send that to the shader land. Now we need to read this one in the shaders because we're not doing that at all right now. So let's go back to the shaders. Let her recompile. Did I attach it? I did. Simple shader. All right, so we don't need to define properties for global variables. We can just like throw them in here. So I seem to remember that you need the uniform keyword for global variables. I could be wrong, but there it is. Anyway. Mouse position. So theoretically, we should have the mouse position in world space now. I actually haven't checked if it's correct. Let's assume it is, and then we'll debug it in case it doesn't work. Okay. Thank you for the follow. Hello, kitties. Okay, so what do we do? Let's get the distance to it as the color, right? Like distance to cursor. Flossed. Floats. What is my ID doing? Distance equals, so we just do mouse position subtracted by world position of the current fragment being rendered, right? And we grab the distance between those two. And that gives us the proper distance we want, so then we just return that distance. And then go back to Unity. It doesn't compile. Oh, right, we don't subtract it. That would be grabbing the length of that vector, but we're doing distance. That seems to work okay so far. The shader compiles. The value is just 0 right now, which is why it's checking the distance toward the center of the world. This looks very artistic. I love this.
It does.
This looks good. Nice. Okay. Anyway, the artist in me is getting distracted. Right. Let's see if it works. Hit play. Yeah, that works. So now we're tracking the mouse position. The mouse position is intersected with a mathematical plane at 0. And then that is sent to a global shader variable, and we can then read from that shader variable in the shader. So now it's like tracking my mouse position. Yeah. So somebody asked about how to make it glow depending on where the where your cursor is. So that would just be using this distance for something else, right? You would like add some color to it or something. So I want to make it a glow. We probably want to invert this one, like 1 minus dist. And we also probably want to clamp this one so it doesn't have negative values. So saturate this one. I would probably want to have a color or something, but yeah, so now I have this glow value, and if we don't do that, and then before we return, we add the glow just straight up on top of this, and then we go back to Unity. So now we have this like glowy thing. Yeah. Is the mouse position global to all shaders since you use static method from shader? Yep, it is. I don't know if this counts as a beginner shading, but could you show us how to make a shade that is affected by other game objects? For example, a water shader with foam at the coastline. That's a very complex thing to do, because there's no easy way to make things affected by other things, because things don't have access to the other things. Usually, so say you do have this shoreline around your thing. The way that you'd probably solve that, depending on, you know, platform and the scale of the game and all of that stuff, you would probably bake some data. Like, you would generate a texture from top down that tells the shaders, you know, where is the coastline. And then instead of, you know, getting access to all the game objects, it just get access to the coastline texture that you generated. And then it can use that texture to make the coastline along the edges of the thing. Yeah, so, well, I can actually make an example out of that. I don't need to do the coastline generation, but this would actually be a good way to talk about, like, textures, because we haven't done texture sampling yet. Okay, let's say you did have a mask for that. So, so the white parts would be islands in your game or whatever it is you're working on. And so forth. So yeah, let's say you have these 3 islands. This is kind of like a height map, say. So okay, we have this texture now. Let's save this and use this for something. Probably you should save it in the actual folder of the game. Thor, what's up? In Army 4, you could use a distance field gradient nodes for the shoreline thing. Don't know if something similar is in Unity. It depends on how you're setting it up. There's no node in... Well, actually, there might be. I haven't used ShadeGraph, but yeah. We're going to do this manually now, but I'm guessing it's like the same thing. It's just that it's abstracted in a thing, right? In a thing called like gradient or whatever. Yeah, okay. So let's say this is our shoreline map. This is perfect. Is it done? No, there we go. Also, I'm realizing I'm dumping all of this into a single shader, like all the different examples. All right, let's go back to the shader. Now we need a texture for this one. So this is how we set up a texture parameter. This is going to be our shoreline texture. This is just the default color in case you haven't assigned a texture. This is the color it's going to use instead. Shoe line. All right, so we do the sampler. Don't need that. There's a cat on your chair. I guess it's not your chair anymore. This cat delivery is very dark. Where's lighting? Hold on. Exposure. There we go. Low frame rate. Thor pair programming. Yeah. Hi Thor. Is he just gonna be here now? Are you just gonna be here now? This glides off screen, just like a short break, cat break. Your cat needs gamma adjustments. Yeah, I'm sorry. Gamma corrected kitty. Right. Oh, I was doing the shoreline thing. Okay, so we have the shoreline texture. Did I remove the texture sampling? Because I keep forgetting how to sample textures. Anyway, let's go to the fragment shader. That's where we're gonna use this. All right. shoreline texture. We need to sample this. It's like text 2D or something. I keep forgetting if it's like a lowercase d or uppercase d. I don't know. O.uv. Or did I call it UV0? I call it UV0. Oh, this is a reserved keyword apparently. So this is the shoreline map. Let's just call it shoreline. Then we can just return. Actually, we can just grab the one of the X component because it's just a grayscale texture. So, yeah, that probably works. But we haven't assigned the shoreline ones. Let's do that, and there we go. So now we have the texture from that we made in Photoshop. We now map that one onto this plane, and the coordinates we use to map that one is the yeah, that's just the UV coordinates, right? So now we can see the case where we're using the UV coordinates to map a texture, which is, you know, the most common use case for UVs, probably. So yeah, now we're actually using this for, you know, its intended purpose, I guess. All right, so now, in your case, you wanted to have like shoreline waves or something that was, you know, dependent on where objects intersected. This texture would have to be generated by you or like or artist authored, and then that would map onto the world of your game. So then you would have like physically islands on top of this or whatever. This is probably not going to work great without compression, or with compression. So I'm going to turn off compression. Here we go. Right. What do we want to do then? Right. Okay. So you wanted to then have waves going out from these, right? If you don't mind me asking, what type of education did you have prior to working on your current game? I've been in the industry for like 8 years at this point. Before that, I did study game design, but I think I'm for the most part self-taught when it comes to Unity and shaders and whatnot. So yeah, I don't know. My education has been like not super influential. It's more like that's been better for like making connections within the industry and whatnot, but yeah. Okay, so now we want something that can like wander along the shoreline, right? So for this, we're probably going to need the time as a variable, right? So we can use time. That's a Unity variable. Time.y is in seconds. So let's say we take shoreline. Right, there's another function that's super useful. Anyway, I'm not going to go through that now. So we have time.y. We can do shoreline plus time. I feel like I should explain time better. Let's make a simpler example. So let's do return. We're gonna just show a simple color. So time.y, and if we just up with this one, it's gonna be like pure white, because this is just in seconds, and there's probably been a lot of seconds that have passed since I started Unity. So this is just way above 1. How do we like remap this to make sure that it like clamps down to 0 to 1? We can use a function called frac. Frac is basically like taking value minus floor of that value. That's the frac function. So what it means is that anything going above 1 or below 0 is going to repeat itself within the 0 to 1 interval. So it's kind of like a sawtooth wave for a linearly increasing value. So if we do this and go back to Unity, you can see that it's like pulsating, right? Is frac cheaper than mod? Most likely, yeah. So yeah, so now we have the time value goes from 0 to 1, drops down to 0, goes back up to 1, and so forth, right? Cool, so now we have time. Time is now a thing. Okay, so how can we use this? So let's see, we have our shoreline, right? So this is a value between 0 to 1 where 1 is the shore and 0 is the water, right? So now we want to have some sort of wave-like thing that goes across it. And now if you remember your maths, if we just do, for instance, return.uv0.y, we get this gradient, right? But we want it to be more wave-like instead of this boring gradient, right? So how do we make waves? Well, there's a function called sine. So we take the sine of that one and then multiply it by some high value. You can see that we're getting this wave type shape, right? If we do 16, you can see that it's like repeating itself. So this is a sine wave expressed itself as a color, right? So we can kind of use this to tweak, to make like these types of repeating wave-like patterns. Also, I like the spheres over here that are also following along. Okay, so now we got that. What else do we want? We want these to not be between -1 and 1, you know, as the sine waves are. So we want to remap this. So a quick way to do that is to, we can add 1 and then just multiply that by 0.5. And that's gonna, it's gonna shift the range and then compress it to be between 0 to 1 instead of -1 to 1. So now you can see that this one goes from 0 to 1 instead of, you know, having this clamped negative thing. Cool, we now have waves. So I guess we should have like parameters for this, like wave size. Is that one. I guess size is kind of misleading because making this higher makes them smaller, but anyway, I guess I can just divide and then it's kind of accurate. I don't know how big this should be. Wait, never mind. I didn't even use wave size. Yeah, that works. All right. Okay, so now we have this wave pattern, but we don't want to apply this to the gradient, right? We want to apply this to the shoreline. So what do? Well, we just grab the thing. We can do float, shape. Let's call it shape. And then we have this one, input the shape there. Now it should look exactly the same. I just call it shape and then pass it in as a variable. Now let's replace the shape with a shoreline. So instead of doing that, we do shape equals shoreline. And now we have this. So now we're starting to get something that's resembling the waves coming out of a thing, right? Okay. So you can kind of see now that we have a texture that we've used to like map this data in a different space than simply, you know, a UV gradient. And we need the texture to get this because otherwise, you know, that information has to be passed into the shader. And if we don't pass it in, we just don't have the data. Yeah. All right. Let's see. I suspect that I might want this one to be linear, right? Actually, 0 difference, never mind. Okay. Okay, so what do we want to do now? We want to move these, right? We don't want it to remain static. So let's toggle back to the one we had before with this thing. There we go. And then let's move this one. And then we want to offset this one. So we had the time variable before, right? So we can simply add that one to the inside of the sine function to offset the sine wave. So then we can do time.y. And then we restart, and now you can see that this one is moving. It's moving a bit slowly, but that's okay. It's a slow shoreline, right? Yeah, go for it. Okay. What's the size of the parents differently sized per island? Oh yeah, the size of them depend on the size of the gradient. That's kind of just the way it's set up right now. All right, so let's see, it's moving a bit slowly. Let's multiply that by something. Maybe too fast. Okay. So that makes sense, right? Now we have these things moving, and now let's switch back to the island shape instead of the UVs. And now we have these things moving out from the shore, right? So yeah. All right, you can see the whole island, or the all the water and the islands are pulsating too, and that's just because the those are included in the whole wave thing. We're kind of just presuming that everything is a wave. Yeah. All right, this is pretty trippy. um, all right. And then I'm guessing we want to use this for like let's see how. Okay, so now we probably want to mask this to make it like make the ground not flash and whatnot, right? So what we can do is that we want to dampen the waves as they move away from the islands. We want to make them be less intense, because now when they're furthest away from islands, the waves are just like going at it, right? So let's dampen them. So let's call this wave amplitude. So that would be this. So if we want to dampen this one, we can take the wave amplitude and then multiply them by the original shoreline texture, or the sample of this one, because it's 1 at the island and is 0 the further away we go to the islands, right? So we can just like multiply that one, and yeah, then we can return the wave amplitude like that. So now you can see that it's no longer flashing out in the water. Now it's just doing, now it's flashing inside of the islands, but not outside, right? If we wanted to make them more irregular, should we add something like a displacement map? Also in questions like this, how do you design your maps? What do you mean by design your maps? I mean, there are different ways of like authoring it, if that's what you're asking. Like you can either do it procedurally, or you can do it by like painting it. Like, I don't know, make a way to paint textures in Unity or something. You could use some texture with some noise distorted a bit. Yeah, could do that. Anyway, okay. Yeah, right now it's like super regular, but that's fine for now. What do I want to do? Do you want me to like keep making this look more like water, or did you like get the example and I should just like do something else, or what do you think? Because if this was applied to the water, there would probably be geometry intersecting the flashing islands regardless, so it doesn't really matter if they're like flashing over there. Ask away, Suzuka. How could you do that effect in a procedural world? You need to generate this texture in that case, which is entirely possible. Yeah. Can you make an object emit light? This depends on the rendering pipeline. If you use surface shaders and you output light and emission and you configure the material to affect light maps or real-time GI, that color will affect the thing. But it's generally, it's complicated. Like, it's, yeah, there are so many, like, the thing is, you can't just make them cast light, but you can make them look as if they're lit, if that makes sense. You can make things on them look brighter, regardless of lighting, that you just add values to it. But yeah. Can you generate a texture in Unity? Yeah, absolutely. I do it quite a lot, actually. But yeah, I think that makes sense. And then of course, if you want this to be like, let's see, we can have like, we can have some colors here. Say we have water, shallow, water deep, and then like wave color, let's make this look prettier. So first we need the watercolor. So that's a float3 watercolor equals. Oh, we need the properties here. There we go. Sorry. Okay. So watercolors. So we do lerp between where it's shallow versus deep, which we can do based on the shoreline texture. So that's going to be the T value for our lerp. And then let's see, it's black where it's deep. So we need to do the deep one first. So water deep, water shallow. And then, so now we have the color of the water, and then we need to blend the waves on top of the watercolor. So then we do another lerp, water with waves, which is another lerp, but between the watercolor and the wave color, based on the waves that we used to return here. Yeah. I think that's it. And then we'll return the water with waves. Then go back to Unity. It's broken. Float3 to float4, right. So float3, no, 4. There we go. Okay, all of the colors are white. So we're blending between white, white, and white, which means we're gonna get the color white. Let's fix that. Oh, I forgot to rename the thing. Wave color, there we go. Okay, water deep should probably be some deep blue, and then we have water shallow, should probably be like cyan or something fresh and cute, and then the wave color can probably be something close to what it already is. I don't know, could make it a bit more slightly cyan tinted or something. I don't know, depends on how you want it to look, depends on your game, art style and whatnot. But yeah. All right. Oh, I guess I could show you a water shader that I made for the game at work. I'm not going to show you the code for that though, but I can show you the shader itself. This is a game at work. Did I close that tab really? Anyway, yeah, I work at NeatCorp. So it's a studio that I co-founded back in Sweden. I'm not in Sweden right now, but yeah, so I work there. We're working on a game called Garden of the Sea, and I did the water shader for this among a bunch of other things. So this is the water shader for that one. This one is a bit more involved because it's got like, you know, it's got depth blending and, you know, reflections and all of that stuff, right? But it also does have a very subtle shoreline here. I don't know if you can tell, but there is a shoreline that's like moving out from the shore here. It's pretty subtle in this one. We didn't want it to be like too intense and whatnot, but yeah. But this one is based on depth, and this one is not like, this one isn't, what was I going to say? This one doesn't have any shoreline, like generated data. So the problem with that is because, is that this looks bad, right? The shoreline doesn't actually physically extend. The shoreline is just a fake thing based on the depth behind the water. So the shorelines kind of only work when you look in this angle, but it's like good enough in many cases. So yeah. Yeah, there's distortion in this one. So there's a refraction in the water. You can see the refraction here on the edge there. But yeah. Yeah, this is fully dynamic too. So this is just like real-time rendered. So like if I move around objects in here, you can see that they all this stuff is like updating and working properly. Yeah, which is the advantage of not having baked data, right? But yeah, the problem then instead is the angle issue. Trees are nice too. Yeah, they're made by coworkers. There we go. Hello. Hello. Yeah. Can you show us the recent reflection in water shady you do recently? The one on Twitter? Yeah, probably. Where is that? Did I save that in a separate scene? The shoreline's the water texture at the boards of it. There's no water texture. There's no shoreline thing that defines where the shoreline's at. Let's see. Where did I put it? Right, I have to duplicate. Let's see, this one should have the reflection. I might have broken this. Hold on. I shouldn't show the code for this on stream. Heck, I think I've just... I think it's just broken. I'm sorry. Nope. Thing broken. Cancel. How do you do Horizon? Big plane or infinite? I think it's just a big quad. This is a very large plane. Yeah. Think about the follow, Gapearn. Yeah, the water itself is just straight up. This is a quad. Anyway, oh, there was another shader in Garden of the Sea that I should show you. That's a fancier one. So this is to show a bit of how the diversity of like all the what you can do with shaders, and this is a very, very different type of shader that I did. Let's see if I can find the thing. This is a hand of the player. This one. This is a very, very different type of shader. This is actually using signed distance field ray tracing. So this is a let's see, there we go. It doesn't fully perfectly blend into the background right now because the depth blending doesn't like jive well with anti-aliasing around the edges. So there are some issues left with that still. But yeah, let's see if I can lock the inspector. There we go. So this is a shader. And again, this parameters controlling the way it looks. It's like, yeah, like all of this is still shader driven, the very same way that we've done before, just more math. And then, yeah. So I have like a bunch of like parameters to control, you know, how soft should the blending be between the blobs, how gloss should the whole thing be, or how glossy, radius of the things. Yeah, so there's a bunch of parameters in case you want to like tweak all of this stuff, or the colors even. Yeah. Because there's a lot of math again. There's a lot of, yeah, a lot of effects. Or a lot of math, yeah. Created one with Metaballs, but it was super expensive. Took the game from 1000 FPS to 60. This is cheap. This is a very small shader. This is just a little socket on your hand. It is expensive, but it's again like a very small area. So yeah, I think it's cheap enough. It might not be cheap enough for depending on like the target platform. So we're probably gonna change it depending on that. But yeah. Did you duplicate the sphere of the mesh to have 2 or 3 of them for this effect? No, this is a single sphere. The mesh itself is, I mean, it's just a, this is the mesh that I'm using. And then, yeah, and then inside of this one, everything is math. I send, like, the information that I have here is the, you know, the direction from the camera to the current position here, and then I have the center point and everything, and then from there on I can sort of like work out all of these geometrical things, and it's all based on distance. And this one is hard-coded to specifically have this amount of spheres. So yeah. But inside of the shader, I have these like, I have a structure where I can define a blob, and then that gets passed into a function that renders it and whatnot, and then combines them all in this goopy way. I also did the thing so I could toggle like quality. So this is much cheaper, but it looks worse, and the bottom blob is kind of broken. Yeah. Yeah. So the sign distance field code is restricted to the sphere area. Yeah, it's only visible within this one. So like if I set the radius to be too big, or like this one, you can see that they're like cut off by that one. So that's why it's restricted. And yeah, it's time-based, so I just pass time into it. Gotta go Google some SDF articles. Yeah, it's super fun. Yeah, the SDF, sign distance field, is the sign distance field rendering. There are a lot of like really good articles on that. But yeah, I don't think I have any like specific tutorials that I followed, but I mean, I guess I could do a tutorial on that if you want to. I think I already did on stream once actually, but yeah, I haven't like done that proper for a long time. I wonder if I still have my projects. Do you use marching cubes on top of it? No, this is just this is a single sphere and then the color out. Marching cubes is for like dynamic geometry and whatnot, but I'm not modifying the geometry of this one. All right, let's see. I don't even know if this scene is working. Yeah, it is working. This is something I worked on together with Ashley, who's in the other room, or Kyperia in chat. So she's been working on this like really cool path tracing, like a renderer for rendering fractals. So we were working on a fractal renderer in Unity. So this is the thing we came up with. So this is also, this is just straight up math in a single quad. The geometry of this scene is 2 triangles. So the rest is just math inside of a shader. And then you get all of this basically. yeah, this is extremely expensive though. But yeah. Yeah, this is the, heck, what's it called? A Mandelbox fractal. Just iterating through for every pixel. But yeah, and you can also like change the way the fractal works to like alter it and modify it and whatnot, to get all of these weird and interesting shapes. Yeah, fractals are pretty neat. But yeah, so there's a lot of stuff you can do there. But yeah, this is signed distance field rendering as well. There's like a distance approximation function to, get the distance to the fractal, and then you just iterate forward and try to make your way through to find, where the surface is at. But yeah, it's pretty neat. In this case, if I wanted to add a collider to it, how would it behave? It would not behave. It would not behave itself. Okay, I can show you the scene. It's actually kind of funny what the scene looks like. Let's see, add scene. Here's the scene. It's literally a camera with a single quad. That's it. So this is the mesh. Feel free to add a box collider to this. So that's a box collider 2D. There we go. We got a box collider. But so yeah. You can see that it's just a single quad in front of a camera, and then the camera moves around the scene like this. The rest is shaders, or one shader. Yeah. Yeah, it's pretty good. Heck, I thought the snapping function was more stable. I know it is pretty stable. There we go. I can get lost in this for so long. It's so pretty. How's Kyperia? She's good. She's resting right now. So she's not here. SDF could be useful to render volumetric smoke or dust clouds. Yeah, the problem is that for smoke clouds and whatnot, they tend to be kind of irregular, and SDFs are kind of by definition very regular, because you have to define them mathematically. So if you want to define smoke, like how do you do that without a texture? And then you get into like very, very expensive noise generation functions, right? You could iterate through a texture, but then there are limits in how many times you can sample a texture. So like it is very difficult to do this correctly. And if you lower the sample rate for a texture, it kind of looks bad in many cases. You can kind of see the pixels and whatnot, so it's very difficult to do this proper. But yeah. All right. Let's see. Was there anything else I wanted to show? I feel like I can show you the game that I'm working on. I haven't showed that. So I do 50% of my time I'm at NeatCorp, working on the Garden of the Sea game that I showed you before. But I'm also, when I stream, I generally work on a game called Flowstorm. I have so many Unities open. Did I just have 3 Unities open? Where'd it go? Flowstorm. We advanced from doing VR to having game engines do VR during the rendering of the world. Yeah, like attach HMDs to your cameras. Fluid Sim, that one looks nice too. Nope, it is unfinished and broken. It's bad. Is there a way to achieve strong Kuwahara effect with that big front? What is that? I don't even know what that is. As a GPU fluid simulation. Best scene switcher ever. I appreciate my scene switcher plugin by the top right. Because I want to be able to switch between the different scenes of this game, right? Where was I? Main menu. So this is a game that I'm working on stream. This is a kind of a hybrid between a platformer and a racing game. So yeah, this is generally what I stream when I'm on Twitch, and I try to keep it very similar to what I just did throughout this whole stream. So what I do is I work in the game, I talk about what I do and why, I answer any questions you might have, and that's pretty much it. So if you're interested in game development or Unity, feel free to follow. So yeah. I should also mention we do have a Discord in case you want to join like other people who are into game dev. So feel free to jump into the Discord. There's a link below the stream in case you want to join. Yeah, so let's jump into Flowstorm. Not that level. So yeah, it's a platformer racing game hybrid. So let's go to my favorite level so far. It's pretty basic at this point. I haven't done like a whole lot of things. It's still not visually polished and whatnot, but anyway. So yeah, it's kind of like a 2.5D racing slash platformer. You control this little rocket. The goal is to make sure that you don't die and reach the finish line as quickly as possible. So you have this little rocket. You can turn left, turn right, and accelerate. And that's basically the controls. The core mechanic of this game is that you can slide on walls. So if you like hit a wall, you can like slide along them like this. So can't see the Discord link. You can have that one too. Okay, so yeah, this is the basics of the controls. But yeah, you die very easily. The only safe part of the rocket is the landing gear. Otherwise, you just explode. Yeah, so everything kind of follows from that. It's very similar to any other racing game, in that, you know, reach the finish line as quickly as possible. Yeah, so this is what I've been working on stream for quite some time. This is kind of the core gameplay so far. Works pretty well. Do you use a Unity network solution? Yeah, I do. I do use Unity. But yeah. I remember that tweet about Propellant Fire Shader. Yeah, love this Fire Shader. I'm really happy with that one. It turned out really well. Let's see. I should probably lower the volume of the game because it is loud. All right. I do have a level with underwater things. I can go to the level editor. I don't think I have like a designed level that has underwater stuff. So most of my time on this game has been spent on the level editor because this is complex stuff. The level editor in Flowstorm is based on these splines, and the level editor is shipped with the game. So this is not for me in Unity. This is for users playing the game, right? So this is not like a plugin for Unity or something. Thank you for the follow. So yeah, this is spline based. You create segments like this. You can move them around, manipulate them the way you wanted to. Reshape your level to your liking, and then you can kind of just keep creating the level until you're satisfied with the way it looks. It's a very interesting level. Then slap in some checkpoints, and then set the starting points, and then you have a level. So the goal now is to just pass through all the checkpoints, and then reach the last one as quickly as you can, to get as good of a time as you possibly can. There we go. There's also multiplayer support. It works kind of the way you expect. You play on a server, you race together, and you have a scoreboard that's shared, and there's no collision between players. It's kind of the Trackmania style multiplayer. Yeah, so that's a level editor. I can also show you the underwater stuff. Underwater stuff is a bit incomplete, but I'm working on it still. So it's a very different type of physics underwater. Like turning the rocket can actually make it turn because of like aquadynamics, I guess. But yeah, that's the water. I also did some very, very basic like water wave simulation stuff. How does a rocket fire shader work? I made a thread on that on Twitter. Where is that? There it is. here is a bit of a shader breakdown for the Rocket Flame. Yeah. But yeah, that's kind of it for the game actually. Right now I'm working on the prop system where you're supposed to be able to like create signs, and then like rotate them and place them in your level and whatnot. I also did the circle shader. I think I tweeted, I did a Twitter thread about that one too, for the circle shader, the rotation gizmo. But yeah. Are you using Unity built-in physics? Yeah, I'm using 2D physics. It's a 2.5D game though, so let me show you what it looks like in 3D. So, like the track and everything, and all of this is like 3D geometry, the curves and whatnot. So all of this is 3D, but the collision is 2D. So, yeah. But yeah, then we've been working on a bunch of shenanigans on stream, like making the checkpoint breaking look like this. It was fun, like trying to make it like shatter like a glass pane or something. I think it worked out really well. That was really fun. Yeah. So how do you do the ship's legs? The legs are just circle colliders. Not just circle colliders, but the collision is just circle colliders. There's a bit of a nuance in the way that they work because the mesh reshapes based on the shape of the track and whatnot. So I can show you what it looks like. There we go. You can see that the feet kind of align to the surface, even if you rotate and stuff. So that's kind of the way the landing gear works, but the actual collision remains the same. It's just the visuals that adapt to the geometry around them. But I mean, it's accurate enough, except for that bounce, which I have no idea why it happened. But yeah, that's the rocket. I want to spend a lot of time making this rocket look good because it's kind of the main character of this game. Like in a racing game, is there really a main character? Well, I guess it's the thing you're racing with, right? How do you adapt the shape? That's a long story, but the long story short, I check for the adjacent geometry and then I rotate the thing and just rotate it to align it with whatever surface I have in the proximity. So it's basically checking proximity to Bezier curves and then it's like aligning it based on that. That's it. Yeah. Math, exactly. Math and data. Thanks for the beginner tutorial you made, by the way. If you continue another time, I'll definitely hear. Yeah, thank you so much for joining. I think, yeah, I have a headache, because I've been going for way too long, and I need to drink more water. I think I had this much water throughout the whole thing, which is not enough. But yeah. So yeah, shout outs and stuff. This is okay, so if you want to follow my stuff, I'm here on Twitch. Heck, thank you so much for the subscription, Darren. I'm here on Twitch. I stream game dev of Flowstorm for the most part, and apparently tutorials now. Yeah, we have a community on Discord, so feel free to join the Discord in case you want to join a community of other game developers. Many of us are also LGBT, so if you want a community that is largely that, then feel free to join. Yeah, so we try to be helpful. We have a dev channel and whatnot to talk about game dev or shaders and whatnot, and I pretty much hang out there all the time. So yeah, feel free to join Discord. Otherwise, I also have a Patreon, so if you want to support me more than just being here, which is definitely awesome and enough in pretty much all the ways, but if you do want to support me a bit more, then any donations or support on Patreon is super, super, super appreciated so that I can keep doing this stuff. yeah, so you can also get all of my like shader breakdowns on Twitter for the most part, where I do like breakdowns of the shaders that I'm working on and how they work. Um, yeah, this has been super fun. Uh, it's been great. Heck, is there anything else I should talk about? Yeah, I think that's it. Other than just like, thank you so much for joining. This was fun. Even though I'm exhausted, I think I did this a bit too much. But yeah, I'll see when I stream next time. But yeah, usually it's around like Thursday, Friday, sometimes Saturday. But yeah, Flowstorm key. Uh, oh right, yeah. If you donate $10 or support me on Patreon at that level, you also get a Steam key for Flowstorm because Flowstorm is actually on Steam. It's not public yet because it's not released. So I should. Let's see. Oh, do we know? Is the person who donated? Are you still on stream? Because in that case, I can just send you the key. Anyway, yeah, so if you want Flowstorm, if you want to try it out, the current version that's on Steam, I should also update it. The current build is a bit not great, but but anyway, it exists. I'm sending a Steam key to anyone who's like being super supportive. So yeah, but yeah, should get a key for, was it Pat McAllister, Steve? Um, but yeah, all right. Heck, I feel like there are so many people here. I feel like I shouldn't stop streaming, but I'm actually exhausted. But I'll be back. And this has been super nice. I, yeah, I very much appreciate this. Feel free to follow me in the future. I'm probably going to do another tutorial at some point. I don't know when. I'm going to talk about it on Twitter probably. So yeah, thank you all so much. And I will see you next time.